Good evening and welcome to The Sleepy Scientist. Tonight's companion is 3i Atlas, an interstellar visitor gliding through the dark on a one-time path. I'd love to know where in the world you're watching from and what time it is there. If calm science helps you unwind, a like and subscribe keeps these quiet stories easy to find. Warm thanks to those already subscribed for the steady support. May this tale be soothing enough to invite sleep. If curiosity keeps the eyes open a little longer, let it be a kind exchange, wakefulness traded for a small bright truth. Now, the question to hold softly: what secret does a traveller from another star leave behind when it passes by only once? 3. I, Atlas, is an interstellar object, born under a different sun, arriving from elsewhere and departing again. Its path is hyperbolic. In the language of orbits, eccentricity greater than 1 means the track does not close, a signature of a guest that will not stay. This matters because such a visitor is a physical sample from another planetary system. Its light and colour hint at composition and texture, and its motion teaches how small worlds are made, nudged and flung free. A few friendly words for the road. Coma is the soft haze that forms when sunlight warms ice and releases gas and dust. Magnitude is just brightness, where smaller numbers look brighter, and non-gravitational nudges are tiny jets of gas acting like quiet thrusters, shifting the course by a whisper. The journey tonight moves simply: discovery and naming, the rulers and scales that make distance and speed feel human. How surveys notice what barely glows, the minimal physics of gravity and escape, the route and safe distance, brightness, activity and colour, calm comparisons with the first 2 recorded visitors, myths kept tidy, possible origins, and the new instruments preparing for the next hello. No rush. Take what lands and let the rest drift past like streetlights on a late train. Imagine a small wanderer crossing a vast room very slowly, almost shyly, and you will have the right beginning for 3i Atlas. It is an interstellar visitor, which simply means it was not made here. It is a body of ice, dust and rock that formed around another star, or perhaps in the cold suburbs of a system we will never see, and then was tossed clear into interstellar space. After ages of drifting through the dark, it reached our neighbourhood and began to write a single line across our sky. That line is the giveaway. Bound objects trace loops. Unbound visitors do not. 3i Atlas is not looping. It is passing through. The plainest description is this: sunlight warms its surface, gravity tugs from far away, and motion follows the quiet arithmetic of orbits. If you could step outside the solar system and watch, you would see a wide, open curve that never closes, a shape known as a hyperbola. In friendly terms, think of a pebble that skims a pond and keeps going rather than sinking. The pebble meets the water, leaves a trace, and moves on. In the same way, 3i Atlas skims our planetary pond, feels the sun, bends a little, and continues into the deep. A careful analogy helps the picture settle. Picture a cathedral of gravity. The sun is the great lantern in the centre. The planets are slow dancers tied to that light by invisible ribbons, and every comet born here is a regular guest who knows the steps. Into this patient dance floor walks a traveller already on its way somewhere else. It bows to the lantern, arcs politely as etiquette demands, and then walks out the far door. It does not learn the steps. It does not join the dance. That is 3i Atlas, courteous to our sun, but never ours to keep. What do we actually see? In practice, astronomers first notice a moving point of light against a background of stars that do not move from night to night. A survey telescope takes short exposures, one after another, and software compares the frames. Stars stay fixed in their grid. The visitor shifts slightly between images. Link enough of these tiny shifts into a track. Point another telescope at the same spot, and a path emerges. When the early measurements are fitted with the equations of motion, an important number appears, the orbital eccentricity. If that number is less than 1, the path is a loop. If it is exactly 1, the path is just at the threshold of escape. If it is greater than 1, the curve is open and the traveller is not bound. For 3i Atlas, that key indicator sits comfortably above that threshold. In other words, it is leaving. The light from such a body tells quiet stories. If warming is strong enough, ices can sublimate, turn from solid to gas, and lift a little dust, making a faint haze around the solid core. That haze is called the coma. With enough dust and gas pushed by sunlight, there can be a slender tail, always pointing roughly away from the sun, not because motion drags it backward like a scarf, but because light and charged particles press upon the freed material. If activity is weak or the surface is crusted with less volatile material, the object can look more like a bare rock, only a point of light with no obvious halo. 3i Atlas may look modest to our eyes, yet modest light can carry generous clues. Brightness rises and falls as distance and sunlight change, and as the body rotates. If the shape is not a perfect sphere, few small bodies are, then different faces reflect different amounts of light. By plotting these small ups and downs in brightness over time, astronomers can tease out the spin rate and get hints about shape. The colour of the light, measured through filters, can suggest whether the surface is rich in certain organics or dust types. These are not loud shouts of truth. They are soft hints collected with patience and improved as more data arrive. Because 3i Atlas is unbound, its speed feels brisk when compared to comets raised in our own backyard. It carries a memory of its birth system's motion layered on top of the sun's gravity well. That extra motion is why it could approach from a direction, and at a pace that look a little unusual if you expect the regular traffic of long-period comets. It is not breaking rules. It is following a different set of starting conditions. The universe never promised that all travellers would enter by the same door. The naming can be read as a story in miniature. The tag tells you 2 essential truths. It is the third interstellar visitor recognised, and it was first flagged by an automated sky survey called the Asteroid Terrestrial Impact Last Alert System, a network that quietly scans for new moving points every clear night. There is something charming about that. An instrument built to guard our home finds a messenger from another one. A real observation also lives in the details you rarely notice. When astronomers report a detection, they include the exact timestamps of each exposure, the positions recorded in tiny slices of sky, and the brightness to a few decimals. They worry over atmospheric blur, the way a star's image spreads a little in poor seeing, and the tiny biases of a camera's pixels. They cross-check with other observatories to make sure the same moving point is being followed and not a trick of noise. As these measurements accumulate, the orbit solution tightens. An early path can wobble within a wide corridor. With more nights of data, the corridor narrows until the fate of the traveller, bound or not bound, is clear. There is a gentle nuance worth holding. Activity can act like a set of weak thrusters. When gases escape unevenly, they push a little, and that can tweak the path in subtle ways that pure gravity would not. Interpreting those tweaks demands care, because you do not want to mistake a jet's whisper for a grand new force. Likewise, brightness can be deceptive. An object that looks quiet may be active in ways our instruments barely register, and an object that looks lively may simply have a dusty surface that reflects efficiently. Patience and cross-checks are the remedy, not drama. The cleanest truthful picture, then, is both simple and generous. 3i Atlas is a small body from elsewhere, most likely icy, following an open path that bends near the sun and does not come back. It glows faintly, perhaps with a soft veil if warmed enough, and its light carries hints about surface and spin. We know it is interstellar because the geometry of its motion requires more energy than a local loop allows. We watch it by watching the way a single point of light refuses to behave like a local. It visits, it teaches, and it moves on. Hold that image the next time you glance at a quiet sky, a traveller courteous and brief, making a single graceful bow to the sun before the darkness opens again and the long road resumes. Names in astronomy are little maps. They tell you where an object fits in the story, who first spotted it, and what kind of thing it is. The designation 3I Atlas carries all three clues in a compact line. The letter I stands for interstellar, a category created when the first visitor from beyond the sun's family appeared and needed a home in the naming system. The numeral is a serial counter. The word that follows celebrates the discoverer. Put it together and you have a simple sentence. The third interstellar object confirmed. Found by the ATLAS survey. Why invent a new letter at all? For a long time, the sky's wanderers fell neatly into familiar drawers. Comets wore tags like C for non-periodic or P for periodic, and asteroids followed their own catalogue rules. Then came a surprise. An object that was neither a periodic comet returning on a long leash nor a local asteroid passing through on a closed loop. Its motion said with quiet confidence that it was unbound, an outsider merely visiting. The International Astronomical Union, keeper of the labels, added a new class with a clear flag. I for interstellar. That single character carries a lot of meaning. It tells observers, students, and software that the usual expectations do not apply. The path will not close. The object has no home orbit here. The counter before the letter matters just as much. 1 I Oumuamua and 2 I Borisov mark the first two entries in the new ledger. 3 I Atlas adds another point to a tiny but powerful list. With each number, the statistics of interstellar visitors shift from a curiosity to a pattern. The third tells us that the first was not a fluke, and the second not merely a lucky repeat. It hints that such passers-by may be common enough that modern surveys will continue to find them. In science, 3 is often the moment a trend stops being a campfire story and begins to look like a rule you can test. The final word in the name Atlas points to the discoverer, the Asteroid Terrestrial Impact Last Alert System. A TLAS is a set of wide-field robotic telescopes running night after night, designed to notice small, moving things that might wander too close to Earth. Its mission is sober: find potential hazards early, but the same vigilance that guards our planet also makes it very good at catching faint, fast guests. The design is clever. Instead of staring deeply at one tiny patch of stars, Atlas sweeps large swathes of the sky quickly, returns a little later, and checks what moved. Stars sit politely in their places. Intruders shift a fraction of a frame. Software turns those small shifts into an initial track, and humans review the candidates worth a closer look. That workflow explains why the word Atlas deserves its place in the name. A discovery is never just the first click on a screen, it is a chain. Survey telescopes capture the first glimmers, pipelines filter signal from noise, astronomers request follow-up from other facilities, positions and brightnesses are measured again and again. With enough points along the path, the mathematics becomes decisive. You solve for the orbit and out drops the eccentricity, the number that describes how open or closed the track is. Less than 1 means a loop. Exactly 1 means just at escape. Greater than 1 means interstellar. When the solution settles comfortably above the threshold, the object earns its I, and the discoverer earns a name beside the counter. There is a bit of poetry in that pairing. Atlas is a mythic figure who holds up the heavens. Atlas, the instrument, holds up a different burden: vigilance. Night after night, it watches for change. Most nights, the changes are local: a near-Earth asteroid, a regular comet, a variable star brightening or dimming as usual. Every so often the pattern breaks. A moving point refuses the usual dance steps, and the orbit wants to be a wide-open curve. That is when a dry line in a database becomes a spark for the whole community. Request follow-up. Confirm the motion. Test the models. and if it holds, write the new name with its telling letter. Because 3I Atlas is also observable as a cometary-looking object, you may see it listed in some places with a traditional comet-style discovery tag as well, a reminder that naming in astronomy carries layers, one layer for physical behaviour, another for orbital class, another for history. None of those alternate labels change the essential truth signalled by the eye. The Interstellar badge does not care whether the surface is quiet or dusty, whether a faint coma is visible or not. It cares about motion and energy, about whether the sun can keep a grip. The importance of the third extends beyond tidy bookkeeping. A trio of interstellar objects lets scientists begin to compare. One showed unusual shapes in its brightness changes, another behaved like a classic comet with a generous tail, a third arrives with its own mix of activity and motion. Even without diving into those specifics here, the message shines through. Nature is varied, and the stream of visitors carries different stories from different birthplaces. The more entries the ledger holds, the better we can estimate how often planetary systems eject small bodies, what sizes they tend to be, and how their surfaces weather the long cold between the stars. Atlas's role also underlines a quiet shift in how discovery works. Once upon a time, many new comets bore the names of patient individuals at eyepieces. Today, a lot of first sightings come from survey machines that never blink and never get bored. That is not a loss of romance. It is a gain in reach. Robotic sentries can scan vast areas quickly, flag hundreds of candidates, and ask the global community for help. The credit line at the end, Atlas, acknowledges that modern teamwork, from designers and engineers to observers and analysts, can spot a faint traveller that older methods might have missed. If you were to condense the story into a single friendly paragraph, it would read like this. 3I Atlas declares, in 3 neat steps, what the object is, where it sits in a very short sequence, and who saw it first. The I says interstellar. The 3 says the third of its kind that met the standard of proof. The Atlas says a tireless survey, built to keep watch, noticed a tiny motion that meant a guest had arrived. The rest of the science grows from that seed, but the seed itself is already a small marvel, a name that doubles as a map, guiding curious minds from label to meaning without hurry or fuss. Astronomers carry a few simple rulers for measuring the dark. The first is the astronomical unit, the everyday stride of the solar system. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometres. If that size feels too grand, picture the Earth-Moon gap as a pocket ruler, about 380,000 kilometres. The Sun is roughly 400 pocket rulers away. Light covers 1 astronomical unit in about 8 minutes, which is a comforting way to imagine scale. When you look at the Sun's light dancing on water, that light left around the length of a song ago. The second ruler is speed in kilometres per second. Earth orbits the Sun at about 30 kilometres per second. That is not a typo. Each second, our world travels a small commute across space. Big planets farther out move more slowly. Small bodies closer in move more quickly. Interstellar visitors often carry extra motion from their birth systems, arriving at tens of kilometres per second relative to the Sun. These are not reckless speeds by cosmic standards. They are simply the natural result of falling through gravity from very far away while already moving in another direction. A third measuring stick is brightness on the magnitude scale, an old but clever system where smaller numbers mean brighter objects. A drop of 1 step in magnitude corresponds to roughly 2.5 times more light. A difference of 5 steps adds up to about 100 times. Because of this inverse system, bright Venus can wear a negative magnitude while faint comets live in the positive teens. Magnitudes look like strange bookkeeping at first, but they allow precise comparisons even when the sky's noisy or the air is unsteady. With those rulers in hand, the word unbound can be explained without drama. In gravity, every orbit is a balancing act between kinetic energy, the energy of motion, and gravitational potential energy. the energy of position in the sun's well. Bound objects have a combined energy that is negative overall, meaning they are trapped in the well and move in closed loops, ellipses that repeat. Unbound objects have a positive total energy, a ticket that lets them come in, curve around, and go back out forever. Think of a deep valley with a surrounding ridge. If you do not have enough energy, you circle inside the valley. If you have just enough, you ride the crest and never quite fall back. If you have more than enough, you cross the ridge and keep walking into the next landscape. Unbound simply means there is no return. Eccentricity is the tidy number that tells you which landscape you're in. A perfect circle has an eccentricity of 0. Any ellipse that closes has a value between 0 and 1. A parabola, the exact escape path, has an eccentricity of exactly 1. A hyperbola, the open curve of a passerby, has a value greater than 1. When astronomers fit observations of a moving point and the solution asks for an eccentricity comfortably above 1, it is the geometric way of saying, this traveller will not be staying. For an interstellar object like 3E Atlas, that greater than 1 signature is central to its identity. Let us anchor the distances. Jupiter orbits at about 5 astronomical units. Neptune sails at about 30 astronomical units. The main belt of asteroids lives mostly between 2 and 3 astronomical units, and the Kuiper belt extends to roughly 50 astronomical units. Beyond that, the hypothetical Oort cloud may reach out tens of thousands of astronomical units, a halo of icy leftovers. These numbers do not need to be memorized. They are simply friendly pegs to hang ideas on. Inner system, middle grounds, outer frontier, and far cold reservoir. For speeds, a few quiet comparisons help. 30 km per second Earth's orbital pace is fast enough to cross a continent in a handful of minutes. The sun's escape speed at Earth's distance is about 42 km per second. That number matters because it separates bound from free. Any object moving too slowly will be captured into some loop. An object with excess speed at a great distance can swing in and leave again. Interstellar visitors carry that extra, called the hyperbolic excess speed. It is the leftover after subtracting all the pull the sun can manage. Now fold brightness back in. As a visitor approaches, it receives more sunlight and may brighten. If ice is warm and gas escapes, dust can be lofted into a coma, which increases the reflecting area and raises the apparent magnitude. At the same time, distance still dims everything. Double the distance and the light spreads over 4 times the area. Astronomers track these competing effects with light curves, plots of brightness over time, to tease apart geometry, activity, and rotation. Even when an object is only a trembling point in a detector, the mathematics of magnitudes can whisper its size, shape, hints, and surface character. Put together, these rulers turn mystery into measurement. Astronomical units lay out the map. Kilometers per second explain the motion across it. Magnitudes translate faintness into numbers. Eccentricity greater than 1 labels the path as a hello and goodbye. With these scales in mind, the journey of an interstellar wanderer like 3i Atlas becomes less a riddle and more a readable sentence in the sky, steady and legible even in the hush before sleep. Wide-field surveys are night watchers with a rhythm. They sweep a patch of sky, pause and sweep it again, then again, returning after a short interval to the same stars. That timing is deliberate. Bright points that belong to the background stay fixed from frame to frame. A nearby wanderer shifts slightly. With a handful of exposures spaced by minutes, software can measure that tiny drift and flag a moving source that barely rises above the noise. It is patient choreography. Look, step away, look again, and compare. The cadence is tuned to catch things that move at earthly speeds through the field of view. Too slow and the object looks like just another star. Too fast and it becomes a faint streak that might be missed unless the system also searches for trails. Modern pipelines do both. They subtract one image from another to reveal fresh changes. They filter out cosmic ray hits and airplane flashes, and then return the image to the system. They and they ask a simple question. Which dots shifted just the right amount in just the right direction? When several detections line up within a short time window, the software knits them into a tracklet, a tiny arc with a sky-plane speed and direction. A tracklet alone is a whisper. To turn it into a sentence, surveys try to find more of them on the same night and on the nights that follow. Link 2 or more tracklets and you can estimate an orbit, even if the uncertainties are still wide. The sky is big and telescopes are busy, so there is a clearinghouse for this effort, the Minor Planet Center. Observers send in time-stamped positions and brightness measurements. The center posts promising candidates on a confirmation page. That page is a quiet alarm bell for the community, inviting other telescopes to look now, not later, because motion quickly carries a faint target away from where you expect it to be. Follow-up comes from all sizes of instruments. Small telescopes with fast cameras can capture fresh tracklets and extend the arc. Medium and large observatories can chase the object with non-sidereal tracking, moving the telescope at the object's rate so the target stays sharp while stars smear into short lines. For very faint sources, astronomers may stack many short exposures, shifting each image before adding it up so the moving dot lands in the same place. This shift and stack method can pull a whisper out of the noise, turning a maybe into a yes. While the world gathers new measurements, mathematicians do what they do best: fit the data. Each fresh position trims the error bars and tightens the orbit. If the path looks like a closed ellipse, the object belongs to our family. If it sits near the razor's edge of escape, more data are needed. If it insists on a wide-open curve, the eccentricity climbs above 1 and stays there. That is the hallmark of an interstellar visitor like 3E Atlas. The conclusion is not declared on a single noisy night. It emerges as independent observers, using different instruments and skies, arrive at the same answer. There is also a treasure hunt in the past. Once an orbit is sketched, astronomers scour archival images to find precoveries, older exposures where the object was present but unrecognized. Each earlier dot lengthens the timeline and makes the orbit solution sturdier. Because modern images are calibrated against exquisite star catalogues, those old positions can be remarkably precise. A single precovery from months earlier can shrink the corridor of uncertainty dramatically, just as adding a distant fence post makes a winding path suddenly clear. All the while, the same frames used for astrometry, pinning down position, also carry photometry, simple measures of brightness through standard filters. If the point looks fuzzier than nearby stars, that can hint at a faint coma. If brightness rises faster than geometry alone predicts, outgassing may be adding reflective area. None of these signs are taken in isolation. Teams compare notes, check for instrumental quirks, and repeat measurements on nights with steadier air. Surveys deserve their place in the story because their design invites serendipity. Instruments like Atlas, Pan-STARRS, Catalina, and the Zwicky Transient Facility do not wait for special events. They create the conditions to notice them. Wide fields catch more sky in fewer shots. Rapid repeats build those crucial tracklets. Automated pipelines never get tired of blinking frames, and global coordination turns a local hint into a worldwide campaign, with observatories trading clouds and daylight across time zones to keep the target in view. Confirmation is a gentle, formal moment, when the linked observations keep returning the same unbound solution, when independent teams see the same motion and measure similar brightness, the case becomes solid. The object earns a provisional tag. Then, if the orbit truly requires interstellar energy, it receives the I designation, and when the counting reaches it, a number. For 3I Atlas, that arc, from first flagged frames to community follow-up to an orbit with eccentricity greater than 1, illustrates how faint lines in the dark become reliable knowledge. In the end, finding what barely glows is less about a single heroic exposure and more about rhythm and cooperation. Cadence reveals motion, linking turns motion into orbits, and follow-up transforms hints into certainty. Out of the hush of 1,000 quiet images, a traveller's story steps forward, a point of light that shifted just enough, often enough, to tell you it was passing through from somewhere else. Picture space as a landscape built from energy. The sun sits at the bottom of a deep valley, and everything nearby feels the slope that leads inward. A small body far away starts with some speed and some position in that landscape. Two simple ingredients tell its fate: kinetic energy, the energy of motion, and gravitational potential energy, the energy of being down in valley rather than on the high plane. Add them together and you learn something profound. If the total is negative, the traveller is trapped in the valley and moves in a repeating loop. If the total is exactly 0, it rides the ridge and never quite falls back. If the total is positive, it crosses the ridge and keeps going into the next country. That single sign, negative, 0 or positive, decides whether an orbit is a closed poem or a one-line note. Escape velocity is the threshold between those stories. It is the minimum speed needed, at a given distance from the sun, to climb from the valley floor to the level plane without any extra push. At Earth's distance from the sun, that escape speed is about 42 kilometers per second. Earth itself circles at about 30 kilometers per second, which hints at the scale of the problem. Add enough speed in the right direction, and a local object could break free. Direction matters because velocities are vectors. A boost opposite to Earth's motion helps. A boost the wrong way may not. Escape is not a single magic number everywhere either. Closer to the sun, the valley is steeper and the threshold is higher. Farther out, the slope eases and the required speed drops. Interstellar visitors like 3i Atlas approach with something extra in their pockets: a hyperbolic excess speed. That phrase means that even very far from the sun, before gravity has done much work, the object already has leftover motion relative to the sun. Imagine walking into a valley while still jogging across the plain. You arrive already moving. That preloaded speed makes the total energy positive from the start, which is why the path cannot close. The sun can bend the route and speed the traveller up near closest approach, but without some way to bleed off energy, friction, atmospheric drag, or a well-timed engine burn, gravity alone cannot capture an object whose account began in the black. The geometry of the track follows the physics like a shadow. The family of possible pairs in an inverse square gravity field includes circles, ellipses, parabolas, and hyperbolas, all called conic sections. Circles and ellipses are the bound shapes, parabolas are the knife edge of escape, and hyperbolas are the open curves of passers-by. The number called eccentricity labels those shapes. 0 marks a circle. Anything between 0 and 1 marks an ellipse. Exactly 1 marks a parabola. Greater than 1 marks a hyperbola, an open curve that comes from infinity and returns to infinity. When the measurements of position and time are fitted, and the solution demands an eccentricity comfortably greater than 1, the sky has written the verdict in its own geometry, unbound. Close to the sun, conservation laws do the quiet heavy lifting. Angular momentum is conserved, which means that as the distance to the sun shrinks, the speed must increase so that the product of distance and sideways motion stays constant. You can picture a figure skater drawing in their arms to spin faster, then extending them to slow down. Energy is conserved too, aside from tiny non-gravitational nudges like gas jets. As the traveller falls inward, potential energy becomes kinetic and the speed climbs. After the turn, kinetic energy flows back into potential as it climbs out again, and the speed falls. Without a mechanism to dissipate energy, the book balances perfectly. The object departs with the same hyperbolic excess speed it had on the way in, only the direction has changed. Why does the path bend at all if escape is guaranteed? Gravity focuses the motion. The sun pulls inward a little more strongly at closest approach, turning the track by an angle that depends on how fast the object is moving and how near it passes. A slow approach allows a wider turn. A fast approach yields only a modest deflection. Either way, for positive total energy, the curve is open. The traveller arrives from one side of the sky, swings around the sun, and heads away to the other side like a stone that glances off a curved shield. Could anything make the path close? In principle, yes, but nature is stingy with those circumstances. A spacecraft can fire a rocket and dump energy as exhaust. A comet diving through a thick atmosphere could lose energy to drag, although that would be a very dramatic end. A near miss with a massive planet can either boost or reduce heliocentric energy, depending on geometry, through a gravitational assist. Capturing an interstellar body into a bound orbit that way is possible in theory, but requires a particular alignment and timing, and even then the odds are small. For a modest visitor on a quiet, sun-skimming arc like 3I Atlas, no practical break waits along the road. The escape idea also explains a few familiar numbers. Earth's escape speed from Earth itself is about 11 kilometers per second. That is the speed a spacecraft needs from near the surface if it wants to leave Earth for good. But ships aiming for the deep interplanetary dark need more, because they must also climb out of the sun's valley. That second climb is why the 42 kilometers per second figure matters for heliocentric escape at Earth's distance. Spaceflight uses gravity assists and carefully timed burns to cheat the bill. Rocks and ice do not get to choose, which makes their fates beautifully honest. If all of this feels a little abstract, an everyday picture can fix it. Think of a skateboarder in a smooth half pipe. Start from low and push gently, and the motion repeats in a loop, left and right, an ellipse in wood. Start from exactly the lip with just the right speed and you skim the edge and never drop back. Parabolic escape. Start with more than enough energy and you fly out of the bowl, touch down on the far pavement and keep going. A hyperbola in shoes. Gravity is the curve of the ramp. Energy decides whether the motion echoes or departs. For 3I Atlas, the minimal physics says this much, and it is enough. The total energy of motion and position is positive. The measured eccentricity sits above 1. The track bends but does not close. Near the sun, the pace quickens, then eases with distance, and no invisible tether pulls the arc back into a loop. The universe allows many kinds of journeys, and this one is a graceful pass-through. A single bow to the sun, followed by the long road back to the wide, cold plain. Draw a calm line across the night and imagine it bending gently around the sun. That is the path of 3I Atlas, plotted not on paper, but in space itself. The geometry is almost head-on to the solar system's usual traffic. Its orbit is retrograde, tilted by roughly 175 degrees, so it comes in against the general direction of planetary motion, like a quiet cyclist gliding along the edge of a slow parade in the opposite lane. That odd angle is a clue in plain sight. This traveller is not from here. Timing gives the second clue. The visitor was first flagged in early July of the year 2025, out beyond 4.5 astronomical units from the Sun, and its course leads it inward to a single close solar pass in late October. That moment, called perihelion, comes at roughly 1 2/5 astronomical units from the Sun, a touch inside the average path of Mars. The shape of that turn tells the story of its freedom. The curve bends neatly and then opens again. Speeds rise and fall along that arc the way a skateboarder quickens at the bottom of a smooth ramp. Far out, 3I Atlas cruises. Nearer the Sun, it accelerates. After the turn, it eases away. Near perihelion, estimates place its pace at roughly 68 kilometers per second, a number you can also read as about 245,000 kilometers per hour. Those are honest, gravity-earned speeds, the natural outcome of sliding through the sun's well on an unbound path. Safe distance, meanwhile, is not a vague comfort, it is geometry. For Earth, the closest approach is widely separated. On this pass, calculations put the minimum distance at no nearer than about 1 3/5 astronomical units, with mid-December bringing a gap of around 1 4/5 astronomical units, roughly 270 million kilometres. That is comfortably farther than the Sun is from Earth. A line that distant is a line without peril. The same story holds for Mars. The visitor's road threads the region near Mars's orbit, but even there the separation is measured in tens of millions of kilometres. Forecasts suggest an early October mist distance of about 30 million kilometres, close by cosmic standards, far by human ones. Think of two ships passing on opposite sides of a wide bay, visible to each other, entirely untroubled. Why safe is truly safe comes from three simple facts that play well together. First, the distances are large and well constrained by many nights of position measurements. Small tweaks to the orbit solution do not erase hundreds of millions of kilometres. Second, the object's total energy with respect to the Sun is positive, which means it is not looping back through our neighbourhood. It is a single guest, not a repeat visitor. Third, the planet's gravity can deflect but not magically grab and redirect a fast, unbound traveller onto a collision path without an extraordinarily precise and unlikely alignment. The quiet math of conic sections and conservation laws leaves very little room for drama. There is also the practical question of seeing it. Because the closest solar pass happens a little inside Mars's average distance, the glare of the Sun will wash over much of the show for casual eyes. Even so, telescopes, both survey sentries on the ground and instruments in orbit, can follow the changing brightness and colour, sorting out what is geometry and what is surface activity. For patient amateurs, the object will likely remain a dim prize, more a plotted point than a spectacle, but it is present all the same, writing numbers we can read. If you like anchors, keep these in your pocket. 1 astronomical unit is the Earth-Sun distance. 3i Atlas never comes closer to Earth than roughly 1 3/5 of that. The perihelion is roughly 1 2/5 astronomical units from the Sun, with the moment arriving in the last days of October. Near that turn it runs at about 68 kilometres per second, and the plane of travel is tipped by about 175 degrees, a near mirror to the planet's direction, which is why its track slices across our sky rather than drifting along with the crowd. Each figure is a soft bell rung by repeated measurements, not a single shout. In the mind's eye, then, the route is simple and elegant. From the deep outer dark the traveller draws near. It curves around the Sun once, at a heedful distance, and glides back outward, leaving Earth and every planet far to the side. A single line carefully measured, becoming a quiet assurance. This is a passing hello, not a problem to solve. Think of a very slow, very quiet firework. There is a small spark at the centre, the solid nucleus, and around it a faint expanding haze. That is what astronomers look for when they ask whether a visitor like 3i Atlas is active. Activity simply means sunlight is warming surface ices enough to release gas, which lifts dust into space. The gas is invisible in ordinary photographs, but the dust reflects sunlight, turning a single star-like point into a soft blur with, sometimes, a tail. From that blur, measured carefully, you can learn a surprising amount. Brightness is the first clue, and astronomy keeps score with magnitudes. On this scale, smaller numbers mean brighter things. A drop of 1 magnitude corresponds to roughly 2.5 times more light, while a change of 5 magnitudes is about 100 times. It feels backwards at first, but the system is wonderfully practical. In a typical observation, a telescope records the visitor and a handful of nearby comparison stars in the same image. Because the stars' magnitudes are well known, you can calibrate the newcomer's brightness against them, correcting for thin cloud or haze along the way. Distance shapes what those numbers do. Sunlight fades with the square of distance, so moving twice as far from the Sun makes the available light fall by 4. The light then spreads again on the way to Earth, dimming with the square of that second distance. That is why comets often brighten steeply as they approach the Sun. They are receiving more light, and if they become active, they present more reflecting surface as dust spreads around them. Many comets brighten faster than pure geometry predicts, often roughly as the fourth power of the Sun-to-comet distance, because the dust production increases as more ices sublimate. The exact rate varies from object to object, but the principle holds. Closer, warmer, dustier usually means brighter. Whether a haze appears at all depends on which ices are present. Water ice needs stronger sunlight and typically becomes vigorous inside about 3 astronomical units. Carbon dioxide and carbon monoxide can sublimate farther out, even beyond 5 astronomical units, stirring a coma when water would still be asleep. If an interstellar traveller carries volatile ices near the surface, activity can begin early and stay gentle. If its top layer is crusty or depleted, it may remain star-like until much nearer the Sun. A true coma is more than a blur. It has a characteristic shape. Close to the nucleus, the surface brightness often declines smoothly with distance from the centre, a signature of steady dust outflow. Astronomers check this by comparing the object's profile to nearby stars. A star, blurred only by the atmosphere and optics, has a tight point spread function. A comet with a coma has a profile that is wider and shallower. If the blur is real, measuring how much wider it is helps separate the dust light from the nucleus light. That separation matters because a bright coma can make a tiny nucleus look deceptively large. Tails add another layer of information. A dust tail curves gently, shaped by sunlight's pressure. An ion tail often looks straighter, guided by the solar wind and pointing almost directly away from the Sun. Tails do not trail behind the object like a scarf in the wind. They point away from the Sun regardless of the direction of travel, which is why a comet can appear to have its tail ahead of it when geometry demands. When the Sun-object-Earth angle lines up just right, forward scattering by fine dust can make the whole scene brighten dramatically, a kind of optical silver lining. Activity is not just a picture, it is also a force. Gas jets act like tiny thrusters, producing accelerations too small for the eye, but large enough for precise orbit fitting to notice. If the measured positions keep deviating in a consistent way from a purely gravitational path, non-gravitational terms are added to the motion model. Detecting that nudge is strong evidence that gas is escaping, even when the coma is faint. Those same jets can torque the nucleus, speeding up or slowing down its spin over weeks or months. In extreme cases, spin-up can pull a loose object apart. In milder cases, it simply changes the timing of the light curve flicker. Colour and spectra turn brightness into chemistry. Through broad filters, many dusty comets look slightly reddish, a hint of complex organics and weathered grains. With spectrographs, faint emission bands from fragments like cyanogen and hydroxyl can appear, tracing gas production. Even when an interstellar visitor is too dim for detailed spectroscopy, colour indices, simple differences between filters, can suggest whether the dust grains are coarse or fine and whether the surface is neutral or reddened. Because activity can masquerade as size, astronomers use careful tricks to estimate the nucleus. High-resolution images may reveal a sharp central peak, the point-like nucleus, inside the broader coma. By modelling and subtracting the coma's expected profile, you can back out the likely brightness of the solid core and place limits on its diameter. There's also a handy shorthand for dustiness called AF-rho, said like AF-rho, which condenses albedo, dust production, and the size of the measuring aperture into a single number with units of length. Bigger values generally mean more dust in the coma. It is not a perfect measure, but it lets observers compare results from different nights and telescopes on a common yardstick. Sometimes activity hides. A body can be shedding gas that is too tenuous to glow strongly, or the dust grains can be large and dark, making the coma low in contrast. In those cases, variability becomes the clue. If the brightness undulates with a rhythm that does not match the expectations from distance alone, rotation and patchy jets may be at work. Conversely, a steady, geometry-driven brightening without extra fuzz suggests a quiet, possibly rocky surface, or an icy surface protected by a mantle of dust. All of these pieces, magnitudes, profiles, colours, small orbital nudges, combine into a personality sketch. A soft, expanding haze and a dust tail imply accessible ices and a surface that yields to the sun's touch. A near-stellar profile with a clean light curve suggests a crusted or inactive exterior. A forward scattering surge hints at fine grains, while a stubbornly reddish colour points to weathered dust. None of these signs, taken alone, writes the full biography, but together they turn faint fireworks into a readable message. For a traveller like 3i Atlas, the message is the prize. Activity, if present, tells of composition and texture formed under another sun. The way the coma grows or fails to grow hints at how its surface has aged during a long drift in the cold. The tiny pushes of escaping gas, recorded in the mathematics of its path, whisper about vent locations and spin. Even when the whole show is little more than a smudge and a line, the light is eloquent, and with patient measurements the night sky yields its quiet, quantitative poetry. Picture a snowball with tiny steam vents turning slowly in sunlight. Each vent exhales gas that acts like a miniature rocket, nudging the snowball in whatever direction the vent points. That is the essence of non-gravitational motion for an active cometary body. When ice is near the surface of 3i Atlas warm and sublimate, escaping molecules carry momentum away. Dust grains hitch a ride and add a little push of their own. None of these pushes are dramatic. They are gentle, steady breaths. But across weeks and months they shift the track enough that careful measurements can feel the difference. Astronomers describe the direction of these nudges in a simple local frame tied to the orbit. One axis points directly away from the sun, one lies along the path of motion, and one is perpendicular to the orbital plane. A push away from the sun slightly alters how near or far the object falls at each moment. A push along the path acts a bit like a tap on the accelerator or brake, changing the timing and stretching or shrinking the size of the orbit solution. A push out of the plane tips the path, tilting the track by small angles that add up over time. Even if gravity dictates the broad hyperbolic sweep, these small, thruster-like effects can fine-tune where the traveller appears night by night. How strong are the pushes? Typical accelerations inferred for active small bodies are tiny, many millions of times weaker than Earth's gravity at the surface, and a very small fraction of the sun's pull at the same distance. Think of the weight of a feather resting on a moving train. The feather cannot steer the train, but under the right circumstances it can be measured pressing on the window. The effect grows when activity is vigorous and fades when the vent's quiet. Composition matters too. Water ice becomes lively nearer the sun, while carbon dioxide and carbon monoxide can work farther out. So the same object may be more responsive at one part of its passage than another. Turning those ideas into numbers requires a model. The classic approach is to keep gravity as it is and add 3 small terms, one for each local axis, scaled by a smooth function of solar distance that represents how sublimation tends to rise and fall. The scaling can be tuned for different ices, a water-like curve that brightens inside a few astronomical units, or a carbon monoxide-like curve that activates earlier. Fit the model to the astrometric positions, the precise sky coordinates recorded at exact times, and the software solves for the tiny coefficients that best reduce the residuals, the little differences between predicted and observed positions. The path to that fit runs through the details of observation. In each image, the target is not a crisp dot. It is blurred by air and optics into a point spread function. If a coma is present, the light can be a touch wider than a star's and slightly lopsided. That lopsidedness can bias the measured position toward the brighter side, subtly shifting the photocenter away from the true nucleus. To mitigate that, teams model the profile, compare it to nearby stars, and use small apertures or specialized fits to keep the centroid honest. Because different telescopes and cameras have different quirks, Solutions usually give less weight to outliers and ask for agreement across instruments before declaring a real non-gravitational signal. Outgassing does more than push, it can twist. Vents located off the spin axis exert torques that speed up or slow down rotation. Over weeks, the rotation period may drift by measurable amounts, and in extreme cases, surface patches can shed material, altering the light curve. A changing spin can, in turn, change which areas receive midday warmth, moving the active patches and reshaping the thrust pattern. That feedback is why some comets show asymmetric behaviour before and after closest approach to the Sun. The same real estate is not being heated in the same way on the outbound leg. Not every nudge comes from gas. Sunlight itself pushes on dust and on very low-mass, high-area surfaces through radiation pressure. For large compact nuclei this is negligible, but for fine grains in a coma, and for unusually light, flaky fragments, the effect is real. Thermal forces can matter for bare rocks. As a small dark object warms on its afternoon side and re-radiates heat, the recoil can slowly shift its orbit, a process known as the Yarkovsky effect. For an active, dusty traveller like 3A Atlas, outgassing is expected to dominate while the ices are lively, with radiation pressure mostly sculpting the dust tail rather than steering the nucleus. Because the signals are tiny, uncertainty deserves a gentle, honest seat at the table. Star catalogues used to calibrate images carry their own errors. Atmospheric seeing changes from minute to minute. A trail that is slightly smeared can move the centroid by a fraction of a pixel. To handle that kindly, orbit solvers propagate a full covariance, mathematics that tracks how uncertainties in one measurement relate to uncertainties in others, and they test the solution by removing a night's data and refitting to see if the result holds. Independent teams, using different pipelines and telescopes, act like a truth squad. When several groups recover the same small acceleration with compatible values, confidence grows. Another useful habit is to allow the thrust pattern to shift with time. Some models permit the peak activity to lag behind the moment of closest approach to the Sun, reflecting thermal inertia in surface layers. Others split the scaling into inbound and outbound halves, recognizing that dust mantles can grow and choke vents as the object evolves. These refinements are not for decoration. They keep the model physically plausible while remaining simple enough that the solution does not chase noise. What does a detected nudge imply? First, it is evidence for escaping gas even when images look nearly stellar. Second, the direction and strength of the fitted terms hint at where vents might sit and how the object is spinning. A strong push away from the Sun suggests dayside sources. A strong push along the path hints that the warmest vents face a little ahead or behind local noon. Third, the total thrust budget tells something about how much material is leaving the surface. Small in absolute terms, but meaningful over the timescale of a passage. There are also helpful negatives. If positions remain perfectly gravitational within the measurement noise, that does not prove the surface is inert. It simply sets an upper limit on any jetting. If colour and spectra show no obvious gas features, activity could still be dominated by large, dark grains that are hard to see. And if different teams recover slightly different small accelerations, the cause may be mundane, differing apertures, different seeing, or varying coma structure on different nights. In the end, non-gravitational modelling is less a dramatic reveal, and more the art of listening for a whisper while an orchestra plays. Gravity takes the lead and writes the main melody. Outgassing, radiation, and thermal effects add faint harmonies that, once heard and measured, make the whole piece clearer. For an interstellar visitor like 3I Atlas, those gentle pushes turn brightness and chemistry into motion, letting a quiet smudge of light disclose its vents, its spin, and a fragment of the landscape from which it first learned to breathe. Line up 3 travellers from far away and notice the family resemblance first. Each one carries more energy than the Sun can keep. Each follows an open, hyperbolic path with eccentricity greater than 1, and each writes a single, graceful line through the solar system before vanishing into the dark. All three were found by vigilant skywatchers, some human, some robotic, who blink images of the night and listen for motion. And all three are small, faint, and fast enough that time with them is precious. In the quiet light of those facts, Oumuamua, 2-Eye Borisov, and 3-Eye Atlas look like siblings, distant, brief, and instructive. Now let the differences speak. Oumuamua was the puzzler. Discovered after its closest brush with the sun, it never showed a clear coma or tail in ordinary images. Instead, its brightness swung dramatically as it rotated, hinting at a very elongated or very flattened shape, and its motion revealed a tiny non-gravitational acceleration that looked like a gentle push. The likely causes discussed by scientists included outgassing too subtle to see, unusual ices, or radiation pressure acting on a low-mass, high-area body. With only a short observing window, many questions stayed open, which is why Oumuamua still feels like a riddle that politely walked out mid-sentence. 2-Eye Borisov was the opposite personality, a classic comet from somewhere else. It arrived with a visible coma and a clear tail, grew more active near the sun, and behaved in many ways like long-period comets born in the solar system. Spectra and colours suggested ordinary cometary materials, with some measurements pointing to a generous supply of easily vaporized ices. The nucleus was roughly on the kilometre scale, the tail was photogenic, and observers from small backyard telescopes to the largest professional instruments could follow its story for months. If Oumuamua whispered strange, Borisov said familiar. 3-Eye Atlas, on present evidence, sits between those two poles on the personality chart. Its trajectory marks it as interstellar beyond doubt, and its brightness and colour behaviour suggest activity that may be present but modest, depending on geometry and surface layers. The path is steeply tilted with respect to the planetary plane, nearly opposite the traffic of the solar system, a geometric signature of an outsider. Its closest approach to the sun keeps it well away from Earth, and while it may not become a naked-eye spectacle, the light it reflects can still be weighed and read. In short, less theatrical than Borisov, less enigmatic than Oumuamua, and valuable precisely because it expands the sample. Comparisons sharpen intuition. Start with look. Oumuamua looked star-like in images, no obvious fuzz, no tail, just a point that brightened and dimmed with a large amplitude as it tumbled. Borisov looked textbook cometary, a soft coma surrounding a point-like core and a tail swept by sunlight and the solar wind. 3-Eye Atlas likely shows a profile that can widen beyond a stellar point when warmed, evidence of dust lifting into a coma, yet the display remains faint enough that careful stacking and profile checks do the heavy lifting. 3 looks, 3 lessons. Interstellar space exports both inert-seeming fragments and lively ice balls, with quiet intermediates in between, then listen to motion. All 3 are unbound, but the way they move on the sky feels different. Oumuamua's late discovery meant it was moving away quickly, leaving only a short arc of precise positions from which to infer a lot. Borisov's earlier detection provided a long arc and comfortable follow-up, making its orbit and activity curve tightly measured. 3-Eye Atlas benefits from survey vigilance that flags faint movers farther out than was common a decade ago, giving the community time to plan observations near perihelion and beyond. As detection stretches earlier, the science stretches with it. Rotation rates, colour changes, and non-gravitational nudges can be tracked more calmly. Composition and activity draw another contrast. Oumuamua's lack of obvious gas signatures forced creative hypotheses, from hidden outgassing of hard-to-see molecules to unusual surface properties that let sunlight push more effectively. Borisov's spectra showed the familiar fingerprints of cometary gases and dust, with some ratios suggesting formation in a very cold birthplace. 3-Eye Atlas, being fainter, invites a more forensic approach. Colours through broad filters, careful light curves, and orbit fits that check for tiny accelerations. even limits. No clear gas band detected. No strong non-gravitational term found. Feed the picture by narrowing what the surface can be. What do the differences teach? First, they argue for diversity. Planetary systems seem to eject a wide range of fragments, some dust-rich and volatile, some crusted or depleted, some perhaps compact shards with little exposed ice. Second, they show how selection affects colour first impressions. A bright active comet is easier to notice and characterise. A small inert-looking shard can slip by unless surveys are both wide and quick. The growth of sky monitoring networks means the ledger of interstellar visitors is likely to fill with many types, not just the photogenic ones. Third, the trio reinforces a quiet truth about orbits and evidence. The interstellar label rests on geometry and energy, not on having or lacking a tail. Oumuamua, Borisov, and 3I Atlas all cross the Sun's neighbourhood with eccentricities greater than 1 and positive total energy. Whether they wear a veil of dust or keep a bare face is a separate, equally interesting question, one that speaks to composition, age and surface processing during untold years in the cold. There is also a human lesson hiding in the timelines. Oumuamua arrived early in the era of modern surveys, and its mystery partly reflects the shortness of the window. The community learned, instruments improved, and 2I Borisov became a long-shared campaign. 3I Atlas benefits from that experience. Better pipelines, faster alerts, and a global habit of coordinated follow-up. Each visitor leaves not only data but also better habits for greeting the next. Lay the three side by side and the family portrait looks satisfying. One sibling is the quiet enigma, star-like and swift, hinting at exotic surfaces or subtle thrusts. One is the classic comet from a foreign nursery, rich in dust and gas, comforting in its familiarity even as it speaks of another sun. One is the measured guest with a tilted road and modest glow, a reminder that the cosmos rarely repeats itself exactly. Together they say that other planetary systems build, weather, and eject small bodies in many ways, and that the solar system is open to brief visits from all of them. If curiosity ever tugs while falling asleep, hold this gentle thought. Interstellar objects are not a single kind of thing, but a small crowd with different faces, crossing the same room. Some whisper, some hum, some hardly speak at all. Listen with patient instruments, and each leaves a clue about the worlds that shaped it, and a promise that others are on their way. Begin with the signals that are clearest and kindest to confidence. The path is unbound. Observations of position across many nights fit a hyperbolic orbit, with eccentricity greater than 1. That single fact places 3 Atlas in the interstellar family. The trajectory is steeply tilted to the planetary plane, moving almost against the flow of the solar system, which is exactly the sort of geometry expected for a visitor arriving from a random direction in the galaxy, rather than along our disk of planets. The distances involved are generous. Earth sits well off to the side throughout the passage, and the minimum separation remains hundreds of millions of kilometres. In plain terms, it is a scientific opportunity rather than a practical concern. Brightness behaves in a way that rewards patience. As the sun-object distance shrinks, the reflected light rises as simple geometry predicts, and subtle departures from that curve hint at surface behaviour. Small, regular flickers in the light curve suggest rotation. The size of those flickers implies that the body is not a perfect sphere. Colours measured through standard filters lean toward the subdued, slightly reddish tones common among dusty small bodies that have weathered long exposure to cosmic rays and micrometeorites. None of this is loud or dramatic, but taken together it sketches a consistent picture, a modestly active or gently crusted small world illuminated by a single close pass. Those are the robust pieces. Now label the debates calmly. First debate: activity. Evidence for a coma can be subtle when the object is faint and the solar elongation is small. Some images show a profile just wider than nearby stars, consistent with a thin halo of dust. Other nights, the profile looks essentially stellar. The disagreement is not a clash of worldviews. It is a consequence of seeing conditions, instrument resolutions, and the object's changing geometry. A related question is whether tiny non-gravitational accelerations are present. If gas jets are active, a careful orbit fit may require small extra terms. Detecting those terms reliably demands a long, clean time series from multiple observatories, and even then the answer can hover near the limit of measurability. Second debate: composition. With an object this faint, high-resolution spectra are hard to come by, especially when observation windows are narrow. Some colour indices can be read as dust-dominated. Others leave room for contributions from gases like carbon dioxide or carbon monoxide that sublimate far from the sun. The safe summary is humble. There is not yet a definitive chemical fingerprint, and that is normal for a visitor glimpsed quickly and at distance. Third debate: size and albedo. The nucleus brightness, once the coma contribution is modelled away, can be converted to a size only by assuming a reflectivity. A dark surface implies a larger object, a brighter surface implies a smaller one. Without a direct constraint on reflectivity, diameter estimates come as a range rather than a number. That is not a failure of method, it is an honest statement of what the data allow. Fourth debate: spin state. Light curve sampling suggests a rotation period, but sparse coverage can alias the answer, creating multiple mathematically plausible periods. Changes in activity can also modulate the apparent flicker, confusing the issue. A firm solution usually follows from a longer baseline and coordinated campaigns that watch through different local nights to fill the gaps. Even with those uncertainties, a quiet consensus has taken shape. 3I Atlas is interstellar by orbit, passes the Sun once at a considerate distance, and is not a hazard. It likely carries ices, as most small bodies formed in cold regions do, and any activity it shows is expected to be gentle by the standards of bright showpiece comets. Its colour and photometry sit within the broad family of weathered, dusty surfaces. If non-gravitational nudges appear in refined orbit fits, they will likely be small and consistent with outgassing that never rises to dramatic display. What might new data decide? 3 kinds of observations have outsized leverage. First, deeper spectroscopy near the best visibility windows, even low-signal detections of telltale emission bands, fragments like cyanogen or hydroxyl, or the infrared signatures of carbon dioxide or carbon monoxide, would anchor composition and help separate a dusty crusted surface from one that is gently venting. If the spectra remain featureless, that result is still powerful. It tightens limits on gas production and pushes interpretation toward lower volatility surfaces. Second, precise multi-site astrometry over a long arc. A few months of tightly calibrated positions, especially if observers use small, consistent apertures to minimize coma bias, can reveal or rule out tiny accelerations. A detected push in the direction away from the Sun points to dayside vents. A push along the path reveals asymmetries in how the surface heats and cools. No detected push sets clean up abounds. Either outcome is useful. Third, coordinated photometry for rotation and phase behavior. High cadence light curves over many nights, stitched together across longitudes, can break period ambiguities and show whether the shape is elongated, flattened, or irregular. Measurements at a range of Sun-object-Earth angles probe how the brightness changes with phase, an effect tied to surface texture and grain size. A strong surge at very small phase angles, for example, hints at fine, loosely packed dust. There are bonus avenues. Archival pre-covery images, once the orbit is known, can extend the timeline backward and reduce uncertainties in the path, which helps every other inference. Polarimetry, measuring the polarization of reflected light, can sort coarse from fine grains and shed light on porosity. Thermal infrared measurements, if the object is bright enough in that band, can pin down the size albedo trade by adding a temperature-based constraint. All of this sits under one comforting umbrella. The absence of spectacle is still data. A faint or inconsistent coma tells you about crusts that seal over vents, or about ices that require more warmth to wake. A near-stellar profile on most nights suggests that dust production is low, which in turn whispers about the thickness and strength of surface layers built during long years in deep cold. A rotation period that refuses to settle may be telling you that jets are applying small shifting torques. Even null results, no gas features, no measurable push, shrink the space of possible stories. In the gentlest terms, the ledger at this moment reads like this: interstellar status, secure by geometry; safety, comfortable by distance; activity, present at most at a modest level with room for quiet; composition, consistent with dusty, weathered surfaces; detailed chemistry to be decided by stronger spectra; size, a range tied to plausible reflectivities, awaiting better thermal or high-resolution constraints; spin, indicative but not final, improved by longer and denser monitoring. What new data may decide are the adjectives, not the nouns, the hows and how muches rather than the whats. And that is enough to keep the mind curious while the body rests, letting a small, faraway traveller write a careful line of evidence across a dark and patient sky. Why is it so dim? Because astronomy is the art of counting very few pieces of light that have crossed unimaginable distances and then been scattered by air, dust, and the glow of our own planet. Think of a single candle on the far side of a football field at midnight while a thin fog drifts through. You can see it, but only if your eyes are patient and your expectations kind. Telescopes are the patient eyes. They collect photons, tiny packets of light, into detectors that are exquisitely honest about how little has arrived. Every setup has a sensitivity limit, a faintness beyond which, for a given night and exposure, you're listening mostly to the hum of the background. That background is not empty. The atmosphere has air glow. The moon throws a wash of light across the sky. City glow sneaks in. Even a perfect detector adds its own small hiss when it is read out. On top of that sits seeing, the blurring from turbulent air that swells a point of light into a small smear. The telescope's size matters because a larger mirror gathers more light, but the blur spreads that precious light over more pixels, and the sky itself is never perfectly dark. Faint targets like 3i Atlas live right at that boundary where signal and background hold a quiet tug of war. One way to push the limit is to take longer exposures, letting more photons arrive. Another is to take many shorter exposures and combine them. The second strategy is often kinder. Short frames avoid trailing if the telescope is not tracking perfectly. They reduce the chance that a plane, a satellite, or a cosmic ray will ruin the only long shot you had. When you add many images together, after calibrating them, the true signal grows steadily, while the random noise grows more slowly, roughly with the square root of the number of images. The result is a cleaner whisper. Calibration is the housework that makes stacking work. Observers subtract a bias image to remove the detector's electronic offset, subtract a dark image to account for thermal electrons, and divide by a flat field that evens out pixel-to-pixel sensitivity and dust shadows in the optics. Then comes careful background subtraction. Measure the average sky glow in an annulus around the object and remove it, so only the object's light remains. If the frames are taken with the telescope moving to follow the stars, a moving target will drift. For that case, you align the images on the stars and the stars become sharp while the target trails. For a faint interstellar visitor, you do the opposite. Shift each frame so the target aligns and add them up. The stars turn to small streaks. The traveller pops into focus. This shift and stack trick is a little miracle of patience. How do you measure the brightness once you can see it? Two classic approaches share the stage. Aperture photometry uses a small circular opening around the target to sum the light, then subtracts the local sky measured just outside. It is simple and robust, but you must choose the opening size with care. Too small and you lose the fainter wings of the blurred image. Too large and you swallow extra noise from the background. The other approach is point spread function fitting, which models the exact shape of a star's blur and scales it to the target. In crowded fields or in poor seeing, fitting the shape can extract more truthful numbers. For a slightly fuzzy object with a coma, a hybrid technique helps. Model a point-like core plus a shallow halo and measure both. Noise has personalities. There is photon shot noise, an unavoidable randomness that follows simple counting statistics. Even a steady light arrives in jittery clumps. There is red noise from the electronics. There is pattern noise from imperfect calibration. On windy nights the image dances a little. On hazy nights the transparency changes. None of this means the data are bad. It means the error bars, the little arms on a plotted point, deserve to be there. They are not apologies. They are information. They tell future you and everyone else how much weight a point should carry. Astronomers often set a threshold for claiming a detection, a steady standard like 5 sigma, meaning the signal stands 5 standard deviations above the noise expected from the background. This reduces false alarms, which are more likely than you might think when you search many pixels across many frames. But it also means that very faint objects may hover just below that line on a given night. In that case, upper limits are reported, fainter than this value. Upper limits are not failures. They are fences that tighten the pasture where the truth can graze. When the target moves, another puzzle appears, measuring where it is, not just how bright. A coma that is slightly lopsided can pull the measured position away from the true centre of the solid core by a fraction of a pixel. To keep positions honest, observers use small apertures or fit symmetric models and compare to nearby stars, whose shapes define the night's blur. If several telescopes in different places agree within their quoted uncertainties, confidence grows that a tiny shift in the path is real and not a trick of the light. Moonlight and air mass set the mood as much as mirror size. Observe high in the sky, and starlight ploughs through less atmosphere. Near the horizon it crosses a longer, dustier path and dims more. A bright moon washes out faint comae, especially in blue filters. Thin cloud is the stealthy villain, stealing a little light while leaving the stars still visible. Good practice means watching comparison stars of known brightness in every frame and correcting your numbers if the night is drifting. Colour matters too. A detector and a filter do not see the world exactly the same way as a standard system. Colour terms, small corrections based on how red or blue a target is, bring everyone onto the same scale so different observatories can compare notes cleanly. Sometimes the most honest answer is that the target was not seen to any reliable depth on a given night. That answer still sharpens the story. If a predicted brightening does not appear, perhaps the activity is weaker than expected. If a predicted dimming is slower, perhaps large dust grains are lingering. Null results carve away possibilities just as surely as detections do. For a traveller like 3i Atlas, dimness is not an obstacle. It is a clue. A quiet coma argues for crusted surfaces or higher volatility ices that only awaken far from the sun. A near-stellar profile suggests dust production is low. A light curve with small rhythmic flickers hints at shape and spin. The error bars around those points are the guardrails that keep interpretations gentle and true. As more frames join the stack, the rails tighten, the curve smooths, and the picture that emerges is not a single heroic snapshot, but a mosaic of careful moments. In the end, seeing little is a craft. You respect the limits of your instrument. You teach the numbers to speak by calibrating them well. You welcome error bars as companions rather than intruders, and you let patience do what brilliance cannot. Turn a flicker at the threshold of vision into a trustworthy sentence about a far-away, passing guest. Stories love drama. The sky prefers patience. When a traveller like Three-Eye Atlas wanders through the headlines, a few myths hitch a ride. Here is a calm sweep of the common ones, with the quiet truths they overlook. Myth 1. An interstellar object is a sudden danger to Earth. The truth is unhurried geometry. Interstellar means the path is open, not looping, and that path is solved from many nights of precise positions. Those solutions put wide, reliable cushions between Earth and the visitor. Distances measured in hundreds of millions of kilometres are not guesses. They are the product of repeated observations and sober mathematics. Even small refinements to an orbit cannot turn a far miss into a collision. Gravity can bend, but without an extraordinarily exact alignment, it cannot yank a fast, unbound traveller onto a bullseye. Memorable truth. A well-measured no is stronger than a loud maybe. Myth 2. If there is no big tail, it is not a comet and must be something exotic. Tails are weather reports, not birth certificates. A tail needs gas and dust, and those require the right ices near the surface and enough sunlight to wake them. Water ice tends to liven up closer in. Carbon dioxide and carbon monoxide can stir farther out. If the surface is crusted or dust-armoured, activity can be shy. Some visitors stay mostly star-like, with only a soft haze detectable in careful images, yet still whisper of ices in their light curves and colours. Others bloom into obvious comets. Both belong in nature's catalogue. Memorable truth. Showiness is a choice of surface and sunlight, not proof of origin. Myth 3. The little non-gravitational accelerations mean engines or intent. The sky has its own thrusters. When sunlight warms a patch of exposed ice, gas escapes and carries momentum away. Those tiny jets nudge the nucleus like a long series of feather-like taps. Over weeks, the nudges add up enough that careful orbit fits can detect them as small accelerations away from the sun or along the flight path. Radiation pressure on fine dust also plays a role. None of this implies control. It is housekeeping physics. Heat, vapour, push. Memorable truth. A whisper of gas can move a pebble without writing a conspiracy. Myth 4. Sudden changes in brightness mean a violent breakup or a dramatic turn. Brightness is a dance of distance, angle, and texture. As the sun-object-Earth angle shifts, forward scattering by fine dust can produce a gentle surge in apparent light, like catching sunlight on a windblown veil. Rotation can swing a more reflective face into view, and then away again. Small evolving jets can lift extra dust for a night and then quiet. The path does not need to change for the sparkle to change. Memorable truth. Light can flutter while the orbit stays perfectly calm. Myth 5. Scientists are unsure, therefore nothing is known. Uncertainty is not ignorance. It is a ruler with markings. Error bars tell how tightly a fact has been pinned. A size estimate becomes a range because reflectivity is not yet known. A rotation period has more than one candidate if the data sampling is sparse. A weak gas feature is reported as an upper limit if it sits below a careful threshold. These are not hedges. They are the scaffolding that lets knowledge grow sturdy. Memorable truth. Good science shows its seams so the cloth will last. Myth 6. If it is interstellar, it must be rare and almost impossible to see again. The first word is becoming outdated. Modern wide-field surveys sweep the sky in steady cadences, linking tiny motions into tracklets and calling for follow-up in near real time. As instruments quicken and software improves, the sky yields more faint movers. Interstellar visitors are fleeting for any single observer, but in the calendar of decades they may be frequent guests. The ledger is short so far not because the cosmos is stingy, but because the lights and the lookout have only recently improved. Memorable truth. Better lanterns find more fireflies. Myth 7. If it is faint, it cannot teach much. Faint does not mean quiet. Even when a target is little more than a gently broadened point, The numbers carry voices. Light curves reveal spin hints, colours sketch surface chemistry, profiles tell coma from starlight, tiny deviations from gravity's script reveal dayside jets. Upper limits fence what composition cannot be. The lesson of modern astronomy is that careful measurement turns whispers into sentences. Memorable truth. The hush of the data is where the detail lives. Myth 8. Naming and numbering are just labels for press releases. In fact, the name is a compressed map. The numeral counts how many interstellar objects have met the standard of proof. The letter signals the interstellar class. The Discoverer's tag honours the survey that did the night work. From those 3 parts you can read a biography, where it sits in the family, how it moves, and who first saw the motion. Memorable truth. A good name is a pocket guide to the sky. Myth 9. If it is from another system, it must be wildly different from anything here. Diversity is real, but physics is democratic. Ice sublimates the same way under any sun. Dust grains scatter light according to size and composition, not passport. What varies are the recipes and histories. How much carbon monoxide was available? How thick a crust grew during eons in the cold? How collisions shaped the surface texture? The family resemblance across visitors is not a disappointment. It is how comparative planetology works. Memorable truth. Elsewhere is not alien to physics. It is a new accent speaking the same language. What to keep as the lights dim and the mind drifts? Interstellar simply means the orbit is open. Dimness is a condition, not a verdict. Small pushes are natural, measurable, and informative. Error bars are friends. Names carry meaning. And most of all, a quiet object can still be generous, offering enough clues in its path and light to sketch a truthful portrait. Let the movie plots race the clock. The real night is slower and kinder. A distant traveller passes. The numbers glow faintly, and understanding deepens without raising its voice. Imagine a young star wrapped in a wide thin disk of gas and dust. Within that disk, grains collide and stick. Snowflakes of ice collect and pebbles grow into boulders and then into planetesimals, small worlds too numerous to name. Most never become planets. They are the leftovers of planet building, the rubble that records the recipe. In every active nursery, gravity and time sift this rubble. Some pieces are swept up, some are ground down, and some are hurled away. An interstellar traveller like 3i Atlas is most likely one of those castaways, born in a disk like this, shaped by local weather, then sent outward on a path that does not return. Ejection often begins with proximity to power. Giant planets and natural slingshots place a small icy body on a path that brings it near a massive planet, and the outcome depends on timing and angle. A single pass might nudge the small body into a new, still-bound orbit. Repeated passes, gravitational pinball, can pump up its energy until it crosses the limit and leaves the star entirely. The process is efficient in systems where giant planets roam, especially if those giants migrated through the disk. Migration stirs the planetesimal sea, pushing and pulling swarms of fragments across resonances that amplify encounters. A few are swallowed, many are scattered inward and outward, and a great number are ejected to the dark between the stars. Binary stars raise the stakes. With 2 gravities at play, there are zones where orbits are simply unstable. A small body strays into one of those zones, and the 3-body dance becomes chaotic. In a handful of close passages, the fragment can be accelerated to escape with less help from giant planets. Observations show that binary systems are common in the galaxy, which means this quick ejection channel may be common as well. The cast-offs from circumbinary disks could be frequent contributors to the interstellar population. There is a quieter route too, the birth cluster. Most stars form in clusters, crowded neighbourhoods that live for a few tens of millions of years before dispersing. In that bustling environment, nearby stars pass within a few thousand astronomical units of each other. Those flybys tug on the wide orbits of distant material. An outer reservoir like an Oort cloud analogue can be shaken, sending some bodies inward and some out past escape. Early ultraviolet light from massive neighbours can strip gas from the disk's outer parts, changing which ices survive near the surface and which are buried. The cluster years are turbulent, and many small worlds learn their long fate there, some bound to distant, slow orbits, some kicked free forever. Composition sets the seasoning, but not the plot. A fragment forming beyond the local snowline, where water and other ices are stable, will carry a cold chemistry. Water ice, carbon monoxide, carbon dioxide, and a mix of organics frozen onto dust. If it forms inside the snowline, the surface may be drier and rockier. Later processing can blur the boundary. Repeated close passes by a hot young star can bake the surface and build a crust. Collisions can expose fresher ice or shatter a parent body into shards that rotate oddly and present unfamiliar shapes. By the time such a fragment is ejected, its skin may be armoured and reddened by cosmic rays, while just beneath, ices remain preserved. Whether 3I Atlas wears a halo of dust or looks nearly stellar in photographs, that behaviour likely reflects a history of heating, mantling, and gentle weathering under a different sun. The launch itself can happen early or late. Early ejections occur while gas still lingers in the disk. Gas drag damps some orbits and amplifies others, helping shepherd planetesimals toward resonances with growing giants. Late ejections play out over hundreds of millions or even billions of years as slow, gravitational tugs rearrange a system's architecture. A small change near a large planet, repeated over countless orbits, can eventually become a decisive kick. The solar system's own past likely included a phase when the giant planets shifted their distances, trading momentum and ejecting large numbers of icy bodies. There is no reason to think other systems do not experience similar reshufflings. Can the incoming direction of an interstellar traveller reveal its birthplace? Usually not. By the time a fragment reaches us, its original motion has been stirred by encounters with its home planets, tapped by the star's gravity during ejection, and then gently altered over vast time by weak tugs from passing stars and the tides of the galaxy itself. The path becomes a story written by many hands. Only in rare cases, when an ejection is very recent and the fragment arrives with a velocity close to that of a nearby well-measured star, might a plausible parent be suggested. Otherwise, the responsible system remains an unnamed neighbour in the galactic crowd. Still, the neighbourhood matters in broad strokes. Around cooler, smaller stars the snowline sits closer in, so icy planetesimals can form nearer the star where gravitational stirring is stronger. Around hotter, larger stars, the snowline lies farther out, offering a wide field for icy growth, but also making those bodies more loosely held. Dense clusters, with frequent stellar flybys, should export more interstellar debris per star than sparse regions. Systems with multiple giant planets are efficient ejectors. Systems without giants may trap more debris long term. Over the life of the galaxy, these differences add up. The interstellar population should be a mixed fleet. Some fragments dust-rich and lively, some crusted and quiet, some rocky, some icy, all of them shaped by their local histories before learning the wide road. There are other rarer tales. A close brush with a giant planet can tidally stress a small body, cracking it and changing its spin. A collision can fling off slivers that are oddly elongated or flattened, then darken them with heated organics. A passage through a dense gas ring can strip a surface clean, leaving a bare, reflective crust that acts differently under sunlight. Each of these stories leaves subtle fingerprints in light curves, colours, and the presence or absence of a coma. None alone will point back to a specific star, but together they map the menu of processes that make interstellar fragments varied. After ejection, the journey is long and mostly uneventful. Cosmic rays slowly alter surface chemistry, building complex darker films. Micrometeoroid strikes pint the skin. Temperatures stay low for ages, preserving internal ices even as the outer millimeters harden. When such a body finally crosses paths with a new star, its response, how quickly activity starts, how much dust it lofts, whether jets produce a measurable nudge, reveals the balance between fresh ice and protective crust. In that sense, every interstellar visitor is a time capsule, not only of the place it formed, but of how it has aged in the deep cold. For 3i Atlas, the safest, simplest origin story is this. It was born as one of many planetesimals in a distant disk, likely beyond that system's snowline. It was stirred by giants or by a binary partner, or by the crowded traffic of a young cluster, and over many turns it gained just enough energy to cross the boundary from bound to free. It drifted through starlight for a very long while, its surface slowly toughening. Now, for a brief season, it passes a new sun. Whether it wakes into a faint haze or stays nearly star-like, its behaviour is a quiet letter from a place we cannot visit, stamped by the physics that shaped it and the gravitational game that sent it on its way. Begin with a single, gentle sentence in physics. Escape speed squared equals 2 times the sun's pull divided by your distance from the sun. Said another way, the speed you need to leave and never return is the square root of 2 times g times the sun's mass, all divided by how far you are from the sun. Everything else is poetry around this idea. Here is the same thought in plain bookkeeping. Think of a little ledger that rides with every small world. On one page is kinetic energy, the energy of motion. On the other is gravitational potential energy, the energy of being down in the sun's well. Add them as energy per unit mass, so that the object's own mass does not matter. If the total is negative, you are trapped in a loop. If the total is exactly 0, you balance on the lip. If the total is positive, you have more than enough to climb away forever. Escape is not a personality trait. It is a sign on that sum. Each symbol in the sentence has a friendly meaning. G is the gravitational constant, a tiny number that tells how strongly masses attract. The sun's mass is the big anchor in the middle of everything nearby. The distance R is simply, how far from the sun are you right now? The escape speed at that distance is the tipping point between bound and free. At Earth's orbit, that threshold is about 42 kilometers per second. Earth itself moves at roughly 30 kilometers per second. Those two facts explain a lot. Our world is happily bound, and anything local that wants to leave must find extra speed. Why talk about per unit mass? Because gravity pulls on everything with the same acceleration, small pebble or big iceberg. When the ledger is written per kilogram, the mass cancels out, and the rule becomes universal. A child's marble and a mountain share the same escape condition at the same place. That is why a single equation can describe a comet, a spacecraft, and an interstellar visitor without changing its clothes. Now connect escape to the feel of a real path. Close to the sun, the well is deep and the escape speed is high. Far away, the well is shallow and the escape speed falls. A bound traveller, say, a long-period comet from the solar system's own cold stores, never meets the threshold. Its total stays negative, and the path must be an ellipse. An interstellar traveller like 3i Atlas carries a little bonus called hyperbolic excess speed. Far from the sun, even before the fall begins, it is already moving relative to the sun with a leftover speed that will still be there after the encounter, like a gift card that remains unspent. In the energy ledger, that leftover shows up as a positive total. Positive total means a hyperbola, which is just geometry's way of saying hello and goodbye. There is a cousin to the escape sentence that observers love because it speaks directly to the speed you measure at any distance. It says, in words, your speed squared equals the sun's pull times 2 over your distance, minus the sun's pull divided by the orbit's semi-major axis. For bound ellipses, the semi-major axis is positive. For hyperbolas, it is negative, which makes the second term add. You do not need to remember the symbols to feel the message. As you fall inward, your speed climbs predictably. As you climb out, it falls predictably. And whether the curve closes depends on that energy sign. Every part of this helps make sense of gentle facts. The speed peaks near the moment of closest approach because kinetic energy has borrowed from potential as the object slides deeper into the well. After the turn, the trade reverses. Without a brake, no thick air, no engine, the book balances perfectly, and the traveller departs with the same hyperbolic excess speed it had on the way in, just pointed to a new patch of sky. Escape speed also explains why safe distance is more than a soothing phrase. Picture Earth sitting far to the side while an interstellar visitor passes the Sun. Planetary gravity can bend the track a little more, like an extra hand on the rail, but cannot easily remove the energy surplus needed to capture the object. To trap a fast passerby, you must take away a very specific amount of energy at a very specific moment, usually by skimming a massive planet deep in its gravity or by burning fuel on command. Nature rarely sets that stage for a small, icy traveller. The alignment required is exacting, and the window is small. What about tiny non-gravitational pushers, gas jets, sunlight pressure, thermal recoil? They exist, and they matter for exquisite astrometry, but they are whispers compared with the escape threshold. They can bend the path slightly and shift the timing, yet they do not rewrite the verdict unless the object lingers in strong sunlight for a very long time and vents prodigiously. The energy book notices the small fees, but the main balance still hinges on the sun's pull and the traveller's inherited speed. Each term in the equation also carries an intuition you can hold. The sun's mass says, deeper well. Distance says, steeper here, gentler there. Escape speed says, how fast must I be to never come back if I stop pushing now? Because the formula scales with 1 over distance. A little closer means noticeably harder to leave. A little farther means the ridge is easier to cross. That is why missions fling spacecraft outward in careful steps, stealing a bit of energy from planets through gravity assists. Nature plays the same game in reverse when building the interstellar fleet. Giant planets give repeated shoves until fragments clear the ridge. A final, soft piece ties speed to shape. The energy sign and the curve's name agree, negative and ellipse, zero and parabola, positive and hyperbola. Eccentricity mirrors the same truth with a different accent. Less than 1 is a loop, exactly 1 is the razor's edge, greater than 1 is open. The escape sentence tells where the line sits in that family without sketching a single diagram. Why does any of this help? Because it turns a scene, one faint point curving through a glare, into a readable paragraph. With the escape rule, a measured speed at a known distance says whether a capture is even possible. With the energy ledger, a small non-gravitational nudge can be weighed for importance rather than feared. With the hyperbolic excess idea, the phrase, from elsewhere, is not romance but arithmetic. The leftover speed is the memory of another sun. Said in the gentlest terms, a single equation in words lets the night relax. Escape speed squared equals 2 times the sun's pull divided by distance. If the traveller's motion carries more energy than that threshold requires, the path cannot close. The rest, the brightness, the coma, the tiny pushes, is detail and delight layered on a simple, steady truth. Sunlight is a sampler. It pours across a small world, bounces off grains and ice, and returns with a tint that tells a story. Astronomers catch that returning light through different coloured windows, filters, and compare the brightnesses. Those comparisons are colour indices. A simple example is to measure how bright the object looks through a blue filter and through a red filter, then subtract the 2 values. If the result is positive, the surface reflects red light a bit better than blue, and the object looks slightly reddish. If the result is near 0, the surface is close to neutral grey. If the result is negative, the surface has a faintly bluish cast. These small differences, gathered with care, are the first clues to composition and texture for a traveller like 3i Atlas. Reddish colours are common among cometary dust and many distant small bodies. Long exposure to cosmic rays and micrometeoroids tends to darken and redden surfaces by building complex carbon-rich coatings, often nicknamed tholins. Fine grains also redden the reflected light more than coarse grains, because small particles scatter shorter wavelengths differently than longer ones. Neutral colours can point to larger, darker grains, fresher ice mixed with dust, or surfaces that have been heated enough times to bake away the most delicate coatings. A faint bluish slope sometimes hints at very small, fresh grains lifted recently by activity, or at surfaces with unusual mineral mixes. None of these moods are decisive alone, but they set the stage. Spectra sharpen the picture by spreading the light out into a rainbow and looking for patterns. The reflected sunlight from dust creates a smooth continuum with whatever colour slope the grains prefer. Superimposed on that continuum, gases can glow in narrow bands. In visible light, classic comet signatures include bands from cyanogen and from diatomic carbon, each a set of gentle hums at characteristic colours. In the near-ultraviolet, hydroxyl traces the breakup of water, acting as a stand-in for water production. In the infrared, carbon dioxide and carbon monoxide leave features that betray more volatile ices. Sodium can flash a narrow, bright line under the right conditions. When such features are present, activity is awake. When they are absent down to a firm limit, activity is weak, or the gas is simply too faint to see with available instruments. Dust has its own spectral fingerprints. Very fine, porous grains tend to produce a red slope and strong forward scattering, which means the object can brighten when the sun sits almost behind it from Earth's viewpoint. Coarser or more compact grains often look more neutral. In thermal infrared, warm dust can glow with a broad feature near 10 microns that whispers of silicate grains, rocky ingredients ground fine. The balance of these signals, even when faint, hints at whether the coma is rich in tiny flakes or dominated by heavier, slower dust. Colour indices and spectra can be fooled by geometry, so interpretation must be gentle. The brightness and colour of a dusty coma change with the phase angle, the Sun-object-Earth angle. At small angles, a collective effect among grains can produce an opposition surge, a sudden brightening that can alter apparent colour slightly. At larger angles, forward scattering can boost the blue or red ends depending on grain size and structure. That is why measurements across a range of angles tell a truer story than a single snapshot. Separating the solid nucleus from the dusty veil is another quiet challenge. A coma blurs the light, widening the profile compared with a star. Small aperture photometry can focus on the sharp core, while measurements in surrounding rings capture the dust. By modelling both together, astronomers can estimate the nucleus colour and the coma colour separately. A nucleus that looks neutral while the coma looks red suggests dusty grains dominate the haze. A red nucleus with a neutral coma hints at larger grains in the cloud, or a crusted surface shedding coarser material. Calibration matters as much as creativity. Comparison stars in the same field anchor the colour scale, but they must be chosen with care to match the object's colour, otherwise small colour terms creep into the results. Thin cloud can tilt the measured colours in subtle ways, especially in the blue. Atmospheric bands, like water vapour lines, can nibble at the spectrum unless corrected. Slits on spectrographs can clip a coma unevenly if the seeing changes. Each of these hazards has standard remedies. Observe standards repeatedly, record sky conditions, and compare independent measurements from different nights and instruments. What might colours and spectra suggest for a faint interstellar visitor like 3i Atlas? A slightly reddish slope in reflected light would place it comfortably among dusty small bodies whose surfaces have weathered in the cold for a very long time. A more neutral tone could point to larger grains or to a coherent crust that reveals less of the fine, fluffy material. A detection of cyanogen or hydroxyl would be a clear, calm flag for gas release and surface ice. A clean non-detection sets a useful upper limit and pushes the picture toward a quiet, dust-dominated coma or toward a surface with fewer accessible ices. A strong forward scattering brightening near the right geometry would lean toward very fine grains. A muted response would favour larger particles. Polarization adds a quiet tiebreaker. Reflected light can be polarized, its vibrations lined up in preferred directions, by scattering off dust. The degree and angle of that polarization change with phase angle and with grain properties. A steep polarization curve suggests fluffy, low-density grains. A flatter curve suggests more compact particles. Even a few well-placed polarization points can confirm what colours and spectra only hint. Interpreting all this requires modesty about mixtures. A single pixel of light from a distant traveller is often a blend of signals, a nucleus plus a coma, a range of grain sizes, perhaps a patchy surface where some zones retain ice and others wear insulating dust. When two explanations fit, say, either fine reddish grains or an aging organic crust, the right answer may be some of both. That is not a hedge. It is the physics of small worlds assembled from diverse ingredients and later processed by heat, collisions, and radiation. The most helpful habit is to let multiple small clues agree. A reddish colour index, a gentle forward scattering surge, and a thermal hint of silicates tell a coherent dust story. A nearly neutral colour, a flat phase curve, and no gas bands within tight limits point toward coarser grains and a modest or sealed surface. A faint cyanogen band paired with a slight non-gravitational nudge in the motion would say that vents are present even if the coma stays shy in ordinary images. Each line of evidence stays light on its feet. Together they walk in step. In the end, colours and spectra are not a verdict. They are an invitation. They invite a thought about what the grains are made of, how large they are, how much ice still breathes beneath the skin, and how long the surface has rested in the deep cold between suns. For 3-eye Atlas, those tints and traces will likely sketch a modest palette. Dust a little red from age, gas that may whisper rather than sing, and compositional hints gathered like moth-wing scales on the edge of an instrument's net. Interpreted with care, anchored by geometry, checked against brightness changes, and tempered by error bars, those hints become a fair portrait of material from another planetary kitchen, carried across the dark and offered to our night in quiet colour. Scale is the quiet hero of this story. Headlines love drama in close-ups. The sky prefers wide shots. A simple check of size, distance, and energy puts 3-eye Atlas into calm focus and keeps imagination from outrunning the math. Begin with what cannot happen. It is not on a collision course with Earth. The measured path is an open hyperbola, and the minimum separation sits far beyond the Earth-Sun distance, hundreds of millions of kilometres. That cushion is not a guess. It follows from many nights of positions that agree within small uncertainties. Gravity can bend a fast visitor's track, but, without an extraordinarily precise encounter, cannot suddenly yank it onto a bullseye. This traveller makes one respectful arc and keeps going. There will be no tidal surprises. Tidal effects drop off extremely quickly with distance. The moon and the sun already dominate Earth's tides. A small body far away adds less than a whisper compared with those two. Oceans will keep their regular rhythms, plates will not notice, compasses will not care. There is no mechanism for it to stop, hover, or park. In space, motion persists unless something removes energy. Air drag could do that, but there is no air. Rocket engines could do it, but ice and dust do not carry engines. A precisely aimed skim past a massive planet might, in theory, capture an object, yet the alignment required is so exacting that it is not a realistic concern here. An unbound path remains unbound. No dangerous radiation arrives with it. The object reflects sunlight and sheds faint dust if warmed. It is not a source of harmful rays. Space is full of cosmic particles already, and this visitor does not meaningfully alter that background. Power grids, phones, and sleeping cats remain uninterested. Bright cinematic transformations are not on the menu. A sudden flare in brightness, if it happens, would come from sunlight glinting off dust or from a small outburst of gas-lifting grains. Pretty for telescopes, inconsequential for planets. A brighter smudge is still just a smudge at a great distance. Now, what can happen, realistically? Small non-gravitational nudges may appear in the orbit fit if gas jets whisper off the sunlit side. These nudges act like feather-like thrusters and show up as tiny deviations from a purely gravitational path. They help diagnose vent locations and spin, not danger. Light curves can reveal a rotation period and suggest whether the shape is elongated or irregular. Colours through standard filters can lean a little red or a little neutral, hinting at dust grain sizes and surface chemistry. A faint coma may form, especially near the moment of closest solar approach, as ices warm and release gas that lifts dust. Each of these is a scientific gift, not a practical worry. Could dust from the visitor reach Earth and make a meteor shower? Interstellar meteors do exist, but the geometry for a specific visitor's dust to intersect Earth at the right time is extremely unfavourable. Comet tails are thin, diffuse fans spread along the orbit. An unbound path does not lay down a dense returning stream. A handful of individual grains might wander into the inner solar system, yet any effect would be so sparse and slow that eyes and cameras would almost certainly see nothing unusual. What about brightness in the real sky? Even under generous assumptions, this is a telescopic object for most observers, a plotted point or a soft blur rather than a naked eye spectacle. A large backyard telescope under dark skies might record it with careful technique and stacking. Small instruments will lean on longer exposure and patience. That is a matter of optics, not of cosmic significance. Everyday comparisons help anchor the scale. At its closest to the Sun, the visitor runs tens of kilometers per second, fast enough to cross an ocean in roughly a couple of minutes, but speed by itself is not threat. It is simply the honest payment of falling into and then climbing out of a star's gravity. The nearest approach to Earth remains greater than the Earth-Sun distance. Picture a ship beyond the horizon, visible by radio, not by eye. Light from the Sun takes about 8 minutes to travel 1 astronomical unit. The separation here is on the order of more than a dozen minutes of light travel time. That is not arm's length. That is several neighbourhoods away on the cosmic map. Think of forces the way you might think of sound. Loud forces are nearby and massive. Earth's gravity underfoot. The moon's pull on the seas. The sun's draw on the planets. Quiet forces are distant and small. The tug of a faraway passerby. The push of faint jets on a tiny nucleus. The second kind can be measured with care and turned into knowledge, but they do not make furniture move. Consider risk in 3 buckets: impact, environment, and misinformation. Impact risk is off the table because of the large, well-constrained miss distance. Environmental risk, tides, radiation, magnetic mischief, sits at negligible given the size and the separation. Misinformation risk is the only lively one. Words like interstellar and fast are exciting, and excitement can squeeze out scale. The antidote is small, steady numbers and simple pictures. Open path, wide berth, faint light, short visit. If curiosity enjoys numbers in plain clothes, here are 3 to keep. First, eccentricity greater than 1 means the path does not close. That is the definition of unbound. Second, hyperbolic excess speed is the leftover motion the object keeps even far from the Sun. It guarantees a one-time visit. Third, distance rules everything. Double the distance and sunlight falls by 4. Double the distance and the tug of gravity drops dramatically. These are not decorations. They are levers that turn fear into understanding. The real-world context is gentle. Telescopes on mountaintops and in orbit will collect images and spectra during the best windows. Survey systems will continue their cadences, logging positions that refine the path and secure the safe distance. Amateur observers with capable gear will chase a challenge and share stacked images. Most people will go about their evenings unaware that a traveller from another sun has passed, and that is perfectly fine. The cosmos often writes quiet chapters. There is one more comparison worth holding, because it honours scale in both directions. A single small world, faint and far, will not change Earth's day. Yet that faint point can change what is known. A few dozen good measurements can test how common interstellar debris might be, how dusty grains behave in soft light, how tiny jets nudge a nucleus. The risk ledger stays empty while the knowledge ledger fills. That is the best kind of headline. Low stakes, high learning. If a last simple summary helps, let it be this. What cannot happen? A surprise impact, a tidal oddity, a sudden park and hover, a harmful radiation event. What can happen? A modest coma, subtle orbital nudges, small colour and brightness changes, useful measurements, and the everyday yardsticks, distances in the realm of more than an Earth-Sun span, speeds that sound dramatic but are just gravity being gravity, and error bars that tell everyone exactly how sure to be. With scale restored, the story is steady and kind, a passing hello measured carefully, then a long quiet road back to the dark. Think of 3i Atlas as a postcard from someone else's workshop. A single visitor cannot tell the whole story of its birth system, but it can hint at what was built there, what was left on the floor, and which tools were used. Planetary systems are messy, industrious places. When young planets grow, they scatter leftovers. Some fragments are corralled into distant clouds, some are ground down into dust, and some are given just enough of a shove to leave forever. Each interstellar object we meet is a counted bead on that thread, turning guesswork about ejection into something measured. Ejection rates are the first quiet lesson. Planet formation does not use every grain. It is more like cooking than chemistry, with peelings and trimmings. Giant planets are especially good at flinging scraps away. When a small body passes near a massive world, the encounter can act as a gravity assist, trading momentum between the two. Repeat that dance a few times, and the small body is promoted from a long looping path to a one-way ticket out. Models of young systems routinely expel vast swarms of planetesimals during these shuffling years. The presence of interstellar visitors in our sky says that this kind of housekeeping is not rare. It is a standard step in building worlds. The rate matters because it connects the dust we see around other stars to the rocks we occasionally catch between them. Many stars wear debris belts, wide, cold rings of rubble ground into fine powder by endless collisions. Those belts glow in infrared light and show structure that often hints at hidden planets, shepherding the grains. If debris belts are busy factories for dust, they're also reservoirs for larger chunks awaiting a nudge. An object like 3i Atlas is likely a graduate from exactly such a reservoir. Proof that the conveyor belts of scattering truly run from the nursery to the galactic street. There is a scale lesson hiding there too. A system that expels fragments quickly cannot be overly gentle in its architecture. Multiple giant planets, planets that migrated, or a binary star companion all make ejection efficient. Systems with only small close-in worlds may keep more rubble in long-term storage. By tallying the types of visitors we see, dusty or quiet, coma-rich or star-like, small or sturdier, we learn which family layouts produce which exports. If most arrivals look dust-active, that leans toward icy origins beyond snow lines. If many look inert, that suggests crusted surfaces and long aging in deep cold. Either way, the ledger nudges models toward or away from particular blueprints. Speed and direction add another clue about architecture. A visitor's incoming velocity relative to the sun and the tilt of its path on our sky tell us whether the wider population is well mixed. If the directions look random and the speeds cluster around the motions of nearby stars, that hints at a long, slow diffusion from many birthplaces, not a fresh burst from one local event. That picture is exactly what you would expect if the galaxy is slowly salted with cast-offs from countless planetary systems over billions of years, now fold in debris belts again, because they are the steady, visible cousins of interstellar fragments. High-resolution images have revealed narrow rings, clumps and gaps that almost beg for an unseen planet to explain them. Those patterns are the footprints of gravitational sculpting, a world nudging pebbles into resonances, sweeping some orbits clean while feeding others. A belt that shows strong structure today likely had a lively scattering past. Interstellar visitors are then the long-distance consequences of that past, pieces that found the exit rather than a stable niche. The two lines of evidence, belts and visitors, are a natural pair. One maps what stayed, the other samples what left. Ejection rates also feed a census question that sounds simple and is wonderfully deep. How much stuff do typical systems throw away? If the answer is a little, then visitors like 3i Atlas are rare jewels. If the answer is a lot, then the galaxy is quietly full of wandering shards. Early estimates from the first couple of detections left wide error bars, as they should. As survey cadences sharpen and more visitors are logged, those bars will narrow. The result will flow back into planet formation models, adjusting how often giants move, how strongly they stir, and how heavy the original disks must be to produce the observed export. There are clues for exoplanet layouts tucked into small details too. Non-gravitational nudges measured in a visitor's motion whisper about surface ices and venting. That, in turn, hints at where in its home disk the fragment formed. Ices that wake far from a star favor berth beyond a snow line. A stubbornly quiet surface may mean repeated bakeouts during close passes to a hot sun or long burial under insulating dust. Put statistical weight behind those hints and you begin to tag not just how much ejecta is made, but where in a system it tends to be minted. Binary stars offer another lesson. Two suns mean broader zones where small bodies cannot keep stable orbits. If visitors from such systems show different typical speeds or surface properties than visitors from single-star systems, that difference will sharpen over time as the sample grows. The galaxy is generous with binaries, which means their fingerprints, if present, should eventually emerge. What does any of this mean for the architecture of planetary systems at large? It argues for variety sitting on top of shared physics. Everywhere, gravity plays the same game. Build planets, stir leftovers, sweep some in, and throw some out. The mix of outcomes depends on a few big choices the system made early. How many giants, how they moved, whether a companion star stayed close, how crowded the birth cluster was. An interstellar traveller is a receipt for those choices. You cannot read the store name, but you can see what was bought, what was boxed, and what ended up in the bin. There is a pleasing humility in this line of work. A faint smudge on a detector will not tell you the colour of its home star's sunsets. It will, however, weigh in on whether that star kept its giants on a short leash, whether its cold belt was stirred, and whether its planetesimals were thrown outward in large numbers. It will tell you that planet building is not a tidy process with nothing left over. It is a generous one that litters the galaxy with souvenirs. If a single sentence helps the mind rest on the idea, let it be this. One visitor is not a biography, but it is a data point with an address. Add enough addresses, and a map appears. On that map, ejection rates trace the highways, debris belts mark the towns, and the architecture of exoplanets explains the traffic. 3i Atlas is one quiet dot on that growing map, a reminder that building worlds and losing small pieces of them are two sides of the same creative coin. New eyes are opening on the night, and they are built for faint, fast things. One lives on a Chilean mountaintop with a mirror wide enough to drink in great gulps of sky, and a camera so large it could photograph a city at once. The other will wait in space, looking not for sunlight bouncing off dark rocks, but for the gentle warmth those rocks give off. Together they change the game, deeper, faster and wider, with better chances to greet the next visitor long before it slips away. Begin with the mountaintop. The Rubin Observatory Survey, often called the Legacy Survey of Space and Time, does something deceptively simple, over and over. It photographs enormous swaths of sky, then returns and photographs them again and again, through the seasons and the years. The field of view is huge, the cadence is steady, the images are exquisitely calibrated. From one pair of snapshots taken minutes apart, software can spot a moving point that's shifted by a whisper. From pairs taken nights apart, it can thread those whispers into a track. The result is an alert stream pouring out in near real time, telling the world where something changed and how much. Why does that matter for interstellar guests? Depth and cadence. Deeper means catching smaller or darker objects earlier, when they are still far from the sun and not yet racing away. Faster cadence means linking those early dots into orbits before the trail grows cold. When a moving object's preliminary fit hints at a hyperbolic path, eccentricity greater than 1, alert systems can flag it promptly, and follow-up telescopes can swing to the coordinates, while the target is still bright enough for useful spectra and light curves. The long, regular drumbeat of observations also reduces confusion. With many nights of data, algorithms can tell a real traveller from a spurious blip. Rubin also helps in a quieter way: uniformity. Using the same filters, the same calibration standards, and the same processing pipeline night after night means measurements from different seasons compare cleanly. That makes it easier to see genuine changes in colour or activity, and to measure tiny, non-gravitational nudges as the path evolves. When the survey revisits a region, it does not just take another picture, it adds another sentence to the same book written in the same hand. Now to space. NEO-Surveyor is designed to notice what optical surveys struggle with: very dark objects that reflect little sunlight, and objects lurking close to the sun on the sky. It will look in thermal infrared, where even a charcoal black asteroid glows with its own heat. Measuring that glow directly is a small superpower, because it breaks the old ambiguity between large and dark and small and shiny. With 2 infrared bands and a vantage point away from Earth's atmosphere, NEO-Surveyor can estimate true sizes and pick out targets that would be nearly invisible in reflected light alone. The geometry is a second superpower. Many visitors, and many near-Earth objects, approach from the sunward direction. Ground-based telescopes avoid that glare. A space telescope designed for warm wavelengths and sunward viewing can patrol that blind spot. Where optical surveys say later, an infrared sentry can say now. Early notice transforms everything. It gives time to plan spectroscopy, to coordinate observatories across longitudes, and to catch activity right as it wakes rather than after it has ebbed. What becomes easier with these upgrades? First, pre-perihelion discovery. The earlier a faint traveller is found, the more nights remain for measuring rotation, colour, and any tiny accelerations from outgassing. Second, reliable orbits fast. With dense cadence and powerful linking software, a candidate's path can be pinned down quickly enough to spot the hyperbolic signature without weeks of doubt. Third, composition clues for the dimmest objects. Thermal infrared measurements from NEO-Surveyor pair with optical colours from Rubin to separate size from reflectivity, and to watch how dust production changes with sunlight. Cadence and coverage are the quiet heroes here. Rubin's cadence, pairs of short exposures, revisited on a rhythm that maps the whole accessible sky every few nights, means very little slips through. Sky coverage this broad finds motion at all ecliptic latitudes, not just along the planet's roadway. NEO-Surveyor's coverage focuses on the sunward lanes where optical sentries are nearly blind, scanning those bright directions systematically. Together they shrink the places where a visitor might hide. There is a social cadence too. Alert brokers, software services that digest the fire hose of nightly changes, will filter and tag moving objects, highlighting those with unusual speeds, colours, or preliminary orbits. Amateur and professional networks already practice rapid handoffs. One group flags a candidate, another confirms the motion, a third grabs a spectrum, and a fourth stacks images for a light curve. As the new systems mature, these handoffs become smoother, and the time from maybe to measured shrinks from weeks to days, sometimes to hours. The upgrades even help when nothing dramatic appears. A clean, early non-detection in infrared sets a tight upper limit on size for a given optical brightness. A steady, geometry-driven brightening curve argues for a quiet surface rather than lively jets. A flat phase angle response hints at coarser grains. These are small, sturdy facts that only regular deep coverage can provide. Will every interstellar object become a headline? No, and that is good. Most will remain telescopic whispers. But the rate at which they are found should climb, and the fraction discovered before closest approach should grow. That means more chances to watch activity turn on, more opportunities to measure colours when geometry is favourable, and more time to search archives for pre-coveries that lengthen the orbital arc. With enough entries in the ledger, ejection rates and source regions stop being guesses and start becoming statistics. There is also comfort in redundancy. Rubin does not retire the earlier surveys, it joins them. Pan-STARRS, ATLAS, Catalina, and Zwicky's wide-field cameras will keep sweeping with different tempos and strengths. NEO Surveyor will not be the only eye in space. Other missions and telescopes can follow up in wavelengths it does not cover. The blend matters. A visitor found in infrared can be chased in optical. A fast mover caught optically can be sized in heat. Many small truths beat one big image. If a single picture captures the change ahead, imagine a harbour at night with many lighthouses. Some sweep slowly but very far. Some blink quickly and close to shore. One looks into a bright patch, others avoid. Together they make it hard for a small boat to pass unnoticed. Interstellar travellers are not boats, and the night is very large, but the principle holds. With new eyes and steadier rhythms, the next faint line through our sky is more likely to be seen early, measured well and understood kindly. And when that happens, when a fresh hyperbola appears in the stream, there will be time to breathe, time to point big mirrors for spectra, time to stitch light curves across continents, time to watch a coma form or not form without hurry. The excitement will be real, yet the tone can stay quiet. No alarm, just a new page in a long, careful book, written with better ink and wider margins than ever before. Night belongs to the watchers, the ones who teach darkness to speak, in quiet domes on mountains and in back gardens, where hedges lean like sleepy guards, lenses cool, cameras hum, and red flashlights turn pages without bothering the stars. Long exposures begin with a breath and a click. The shutter opens, the sky pours in, and photons that left a distant object hours ago or centuries settle into a tidy grid of pixels. During a good exposure, the world seems to hold still. Wind softens, voices drop, even the clock on the wall chooses to whisper. Then the shutter closes and the signal is counted. Faint, imperfect, and precious. Long exposures are patience made visible. Guiding keeps the field steady while the Earth rotates beneath. A slow ballet of gears and corrections. In excellent seeing, a star is a pin. In restless air, it is a puff of dandelion. Each frame is the product of a dozen small agreements. Focus found, temperature stable, tracking true, clouds behaving. Calibration frames are taken like scales before a song. Bias to subtract the electronic offset. Darks to catch the thermal hiss. Flats to smooth dust, shadows, and uneven sensitivity. When the raw image appears on the screen, it looks almost plain. Apply the calibrations and the plainness softens. The background levels even out. A faint dot stands where numbers say it should. There is a small, private smile at that moment. Across time zones, another screen wakes. The universal clock that astronomers live by is unromantic and perfect. Coordinated universal time stitching night to night, continent to continent. A message pings a team in Hawaii that an object is clearing trees in Chile. A telescope in the Canaries cues a non-sidereal track, the mount compensating for motion, so the target stays sharp while the stars become short strokes. In South Africa, a cloud sensor blinks amber, then green. Exposures resume and fill a gap that would have stretched a light curve thin. The sky hands off like a relay, and people who have never met share a rhythm as clean as any orchestra's. The choreography is more human than heroic. There are mugs of tea cooling at control room consoles, sticky notes with ephemeris IDs, and the quiet ritual of checking each fit's header. Timestamp correct, coordinates precise, detector temperature steady, air mass acceptable. On some nights, a plane draws a diagonal scar across a frame, and the stack must be adjusted. On others, the moon lifts the background like a tide, and smaller apertures become the friend of truth. Each decision is a nudge toward honesty. Measure the local sky a little farther from the coma, reject that one frame with the wind-smeared stars, keep the same reference sequence so colour terms behave. When a faint traveller like 3i Atlas is on the schedule, the community becomes a ring of small lighthouses. A survey team posts a candidate tracklet. A broker service flags the motion. The Minor Planet Centre lists a request for confirmation with times rounded to the nearest minute, and the predicted path arcing through constellations. Minutes later, backyard observatories respond with stacked images and careful astrometry. The positions measured against rich catalogues and reported to 3 decimal places of arcseconds. A professional facility follows with deeper frames that pull the point from the noise and a spectrum that, even if featureless, sets a useful upper limit. None of these moments makes a headline. Together they make knowledge. Small wins arrive like soft chimes. A pre-covery image appears in an archive from months earlier. Same field, same object, unnoticed until the orbit told observers where to look. The extra dot lengthens the arc and the orbit solution tightens. A long corridor of uncertainty shrinks to a hallway. A night of photometry fills in the wobble between 2 earlier peaks, clicking a rotation period into place. A carefully modelled profile shows the target just a touch wider than nearby stars. A hint of a coma that, once found, others can confirm. A null result, reported with a clean fainter than limit, becomes the fence that keeps speculation from wandering. Each data point has a small weight. Enough points, honestly weighed, lean the beam the right way. Coordination is not only telescopes and timestamps, it is people. Amateur observers keep journals as meticulous as any lab notebook, noting thin cirrus at midnight and a breeze that settled after 1. Graduate students trade code snippets that tame wayward backgrounds. Engineers nurse a cranky dome motor and become the unseen authors of a perfect image. A principal observer thanks a colleague for staying up a little longer to catch one last frame. A colleague in a different hemisphere wakes early to keep the chain unbroken. The strengths are shared, and the weaknesses are shared too, because everyone understands that a long light curve owes as much to persistence as to aperture. Even the language is tuned to care. Words like residuals, uncertainties, and upper limits sound dry until you hear what they prevent. The easy slide from wish to claim. Error bars are drawn not to apologise but to promise. This is how much faith to put in this dot. When several teams, using different telescopes and methods, land their dots within each other's bars, trust accumulates. The plot becomes less a series of isolated notes and more a melody you can hum. Not every night cooperates. Clouds arrive and linger. An all-sky camera shows a sky full of nothing, and the log fills with patient lines, weathered out, no data. On those nights, someone somewhere clears unexpectedly and the chain is saved. A small observatory with a modest mirror contributes a crucial measurement because it happened to have clear air. The feeling is not triumph so much as relief and gratitude. The quiet knowledge that shared effort caught what a single watcher would have missed. When data travel, they gather kindness, Files move from domes to servers to laptops where algorithms blink and plots appear. A figure with points and bars and a modest caption becomes a thread in a paper. The acknowledgements page reads like a star map of people. The operators who checked oil in gearboxes at dusk. The time allocators who granted a window on a crowded schedule. The anonymous referee who asked for one more check and made the result sturdier. Every tidy number has fingerprints. There is a particular hush at the end of a long night when the last exposure finishes and the telescope slews to park. In that hush, the sky seems closer. A visitor from another sun has been watched, not captured. Measured, not tamed. The accomplishment feels both small and exactly right. A faint point moved exactly as predicted, because a ring of night watchers helped each other keep it honest. Hold that thought as the mind drifts. Behind every elegant orbit solution and every careful light curve is a team, scattered across latitudes and languages, passing the sky from hand to hand. Long exposures made with steady breath, time zones linked by trust, and small wins shared until they add up to something larger than any single frame. The numbers are the story, yes, but the story is also the people who stayed up to write them gently. 3 truths fit easily in a pocket and travel well, even through the dark between suns. First truth: Interstellar is a geometric fact, not a mood. A path with eccentricity greater than 1 and a positive energy ledger is a one-time crossing. Arrive, bend, depart. That single decision written into the motion of 3i Atlas is enough to sort fantasy from possibility. It says the visitor does not belong to the sun's long dance and will not circle back for a second ball. It also says something friendlier. The sky is not a closed room. Small worlds can wander in from other workshops and leave again, and their brief company is invitation enough to learn. Second truth: faint is not empty. A soft point of light that barely stands above the background still carries structure, colour, timing, and gently hidden forces. Measure brightness carefully, and it becomes a rhythm that hints at spin and shape. Compare colours through simple filters and dust tells on itself, leaning red or neutral, fine-grained or coarse. Watch the path with patient precision, and tiny non-gravitational nudges whisper about dayside vents and quiet jets. None of this requires spectacle. The art of seeing little, stacking, calibrating, letting error bars speak, is a steady way to turn a smudge into a sentence. Third truth: knowledge is a team sport played at night. Surveys keep a heartbeat that never tires. Follow-up telescopes sharpen the view. Archives donate pre-coveries, and careful math ties the knots. A dozen time zones share the sky as if it were a baton. Small wins, 1 extra data point, 1 tighter limit, 1 clean colour, add up until the story is sturdy enough to lean on. The orbit settles, the safe distance hardens, the activity level finds its level, and the map of what matters and what does not stops shifting underfoot. The quiet triumph is not a single image. It is a community choosing patience over drama. If a forward-looking thought belongs here, let it be about the eyes opening wider. New surveys on the ground will sweep deeper and faster, catching visitors earlier when there is time to listen to their light without hurry. New instruments in space will feel the warmth of small, dark objects that hide from ordinary sight and will watch closer to the sun than ground telescopes dare. Together they will turn rare chance into regular opportunity. The ledger of interstellar guests will lengthen from a short list to a meaningful sample, and patterns will appear, which surfaces wake easily, which stay crusted, which speeds and tilts are common, which are not. The picture of how other systems build and eject their leftovers will move from polite conjecture to statistics with teeth. There is comfort in how small the stakes are and how large the meaning can be. For Earth, 3i Atlas is a distant passerby, a safe geometry traced and checked. For knowledge, it is a specimen pulled by gravity onto a lit stage for a single act. Even its quietness is a clue, A modest coma or none at all tells of crusts and ices shaped under another sun and weathered in long cold. A hint of colour, a thickness of dust, a faint nudge in the orbit. Each is a bead on a string that connects laboratories to landscapes no ship will visit. It helps to recall that stories about the universe do not need to end with exclamation marks to be worth remembering. A measured hello can teach more than a shouted surprise. Think of a naturalist with a notebook at dusk counting moths by the porch light. Most flutterings are ordinary, but every now and then a wing pattern appears that has not been seen here before. Nothing in the yard changes, everything in the ledger does. Interstellar visitors are the sky's version of that dusk, new patterns in familiar light, found because the porch lamp is steady and someone is watching. Allow the mind to hold one last image of scale and honesty. The sun's gravity shapes an elegant valley. Three-Eye Atlas skims the contours, speeds where the slope steepens, slows as it climbs away, and never once pretends to be anything but free. Telescopes and people do not try to tether it. They keep time, put numbers to light, and let the path be the path. There is a generosity in that restraint, and it is the same generosity that makes science restful to hear at night. Truth without urgency, curiosity without alarm. If a single sentence should remain when the details fade, let it be this gentle pair. The universe is open, and attention is enough. Open, because small worlds can cross from star to star without permission. Enough because a careful eye and a clean measure can gather meaning from a faint line in the dark. The next visitor will come, and there will be time to notice. The next survey will sweep, and a quiet alert will ping across the world. Another dot will shift against the grid of stars, and another story will walk in with it. Let the shoulders loosen, let the numbers assemble themselves into a simple shape. A traveller from another sun has passed, and three truths fit back into the pocket where they belong. Interstellar is geometry, faint is full of information, and patience shared becomes knowledge. The rest can wait for morning. If sleep arrives now, it arrives on friendly terms, with a last unhurried question floating like a small lantern in a great room. What might the next quiet visitor teach when it crosses our sky only once? The mind returns to the first image, a snowflake of ancient ice and dust crossing the space between stars, drawing a single silver thread through the dark. Three-Eye Atlas has sketched that quiet line and kept going, a courteous bow to the sun and then a graceful exit. Hold that small, shining picture a little longer. A traveller from another sun passed once, unhurried and unbound, and the night allowed a clear look without alarm. The gentle truths stay simple. Interstellar is geometry. Arrive, bend, depart. Faint is not empty. A soft point can carry colour, rhythm, and meaning. Patience shared becomes knowledge. Long exposures, steady hands, and careful notes turn whispers into sentences. None of it required spectacle. All of it rewarded attention. Let the shoulders relax and the breath lengthen. There is no need to replay every detail. The story has already settled into place like dew on quiet grass. A safe distance, a line that does not close, a modest glow that still told its tale. Instruments listened. People across time zones tended the firelight of data. The sky, as usual, remained generous and calm. If calm science before sleep brings ease, a gentle like and subscribe keeps this harbour easy to find. Warm thanks to those already subscribed. Steady curiosity is the tide that carries these slow stories forward. If it feels comfortable, share in the comments where tonight's watching happened. By a bedside lamp, on a last train, under a soft blanket, or with the room dark and the window a little open. Small notes make a quiet map of listeners under the same sky. Let the image from the beginning return once more. A smooth pebble rests in the palm of the mind, the question asked at the start. What does a traveller from another star bring when it passes by only once? The answer is modest and kind. It brings a reminder that the universe is open. It brings a chance to practice attention. It brings an evening where numbers turned into calm understanding, then folded back into the dark. If the eyes feel heavy, let them. The story is patient and needs nothing more. The silver thread fades, the room settles, and the night takes on that soft, familiar hush. Sleep can arrive whenever it chooses, with the last picture untroubled, a quiet visitor, a safe distance, a gentle bow, and a long road continuing through the dark beyond the window.